on robotic tactile sensing and robotic perception, and we're excited to hear her talk this morning. So please join me in welcoming our speaker.
Thanks very much for the nice introduction, David. And it's really a great pleasure to be here to introduce our work. So as David just mentioned, so actually comes from another community, robotics. It's very different. So I'm here, hope to talk a little bit more about our progress, our work, but also our questions. We are looking for answers from this community. So as a robotist, we work with robots, and a common things we want the robot to do is frequently interact with the real environment, with the physical environment. So, which means like something probably like this. So we know that as humans, there's lots of information we want to understand, like where are those fruits or vegetables? Can we pick some that is good, that satisfy our need, and put that in the basket? So as robotics, we ask ourselves every day, can we make a robot to do a similar things? So of course, there's lots of challenge. So of course, and perception is one part of it, and especially touch. So for example, as a human, we touch an avocado to understand what's the hardness of it, so that is it too raw for us to eat in a few days, or is already rotten, so we cannot eat that already. Of course, there's again, as a robotics, we are asking ourselves every day, like, can we make a robot doing this? So to do this, let's firstly take a look at what are existing technologies for touch sensing. So this is a typical tactile sensors that is already commercialized, produced by Wise Robotics. So this kind of sensor can measure the distribution of the contact normal pressure with a spatial distribution of 5 millimeters. So here it shows an example like a human is touching this robot fingertips, these dark blue areas, and the other side is the readings from the tactile sensors. So you can see that is the greatest structures, and we have some very strong readings in the middle, and a little bit weaker readings on the peripheral areas. So this exactly match this round shape of a human's fingertip. So with this kind of sensor, robot can do a lot of things. So for example, this is a typical things we're thinking about whether we can make a robot to grasp delicate things gently without crushing them. So here is the help of tactile sensors at this fingertip of this robot fingers. It can detect the contact immediately after this contact happens, and can detect like what's the force, what's the distribution over this area. So that can help the robot to control the force and make a gentle touch without crushing this egg. But of course, if we're thinking about this like a very complicated supermarket case, we want the robot to be able to understand more about touch. So the first challenge is that how can we get a better sensor to give robot more information about what is happening on this contact area? So one solution we are trying to propose is a new kind of tactile sensor called gel sight, which is very special in that it can provide very high details, high resolution details of the geometry that the robot is touching. So the design of the gel sight sensor is actually a textbook structure of introduction of like how photometric stereo work. But instead, like making an optical setup, we're making a physical setup. So the central part of the sensor is a piece of clear elastomer, which is painted by this very fine and reflective membrane. So when something is contacting this elastomer, the elastomer will deform as the shape of these external objects. And that will make the change of, make some change of the shadings of this reflective membrane. And we can put the camera in the back, on the other side of this elastomer and capture how this shape changes. And we also put the light, control the lighting environment, put them shining from the different directions with different colors on these reflecting membranes, so that according to the color of the shadings, we know where is the direction of the incoming light. And then just by using this photometric stereo method, we can reconstruct the 3D shape of this contact surface. So now since here we are using a camera has a very high spatial resolution, we can see so much details about this contact surface, and we can see so much details about the object's geometry this sensor is touching. So of course, this is just a principle how it works in practical, since if we are going to introduce this sensor to a robot, there's lots of practical challenge, like how can we make the sensor really compact? How can we squeeze everything together? How can we make the camera works very, very fast? So Long story short, we find a way to make it, and finally we try to squeeze all the optical components into a small area and make a shell to cover everything and make the sensor like that. And this sensor is already small enough that we can install that on a robot gripper's finger and make the robot go around and touch different objects and detect what it is touching. So another thing we have been doing is to paint some black markers on the surface of this soft elastomer and track the motion of the markers. They're extremely helpful in telling the planar deformation of this soft elastomer. For example, when a human is twisting around on this surface. So on one hand, we can see the geometry, which is the fingertip of this human. But on the other hand, we can also see this very clear rotational patterns by tracking those black markers. So that tells about the contact force and the torque. So specifically, we found that when there's different type of the force and torque, the markers will make different patterns of the motions, and the magnitude of the motion of the markers is linear to the magnitude of the force or torque. So this shows how the sensor works. Now we have this very fine, those very fine information about contact geometry as well as the force. How can that help robots? So the most straightforward thing is that we can tell robots what is touching by detecting the shape and texture. So especially can even tell the fine details of the textiles yarn patterns. So here shows an example one of our early work of using a robot to grasp different type of the clothing. And we can see the textures and this overall geometry change during this squeeze process. Everything is very clearly read from the gel set image. And the robot can learn a lot of that, not only what kind of material it is, but also what's the physical property of those clothing, especially how we shall wash those clothes. So with this kind of information, we actually asked the robot to do a little bit more, ask it to touch the clothes, learn how to wash the clothes, can we use a washing machine with warm water, or shall we use cold water, or can we only use a hand wash? So the robot will touch the clothes, detect what's the washing method, and drop the clothes into the corresponding basket. So now we have a question. So of course, it's very easy to detect those detailed geometry, and that's very helpful. But is that possible? Can we have a deeper understanding about what is happening on the contact surface, or deeper understanding about what's the property of all the objects? So we take another look from human, especially at this process of human touching an avocado. And as we talked about earlier, so the most important thing we are trying to figure out here is how hard is this avocado? So actually during this touch, the human's fingertip is deforming. And we are basically using the deformation of this human's fingertip to understand what is the physical interaction it is like, and which infers lots of information about this object itself. So especially this human's fingertip is always soft. It's made of a soft skin and soft flesh below that. And during this contact, usually this soft fingertip will get pressed, compressed, and stretched. And we use lots of this kind of physical change of the information to tell us some deeper what is the interaction mode is like, and what is happening inside these objects, and what's its property about these objects. So the good thing is that the gel set is actually making of a similar structure. It has a very soft gel pad, and they also deform during the touch. And we can monitor very clearly about what is happening on the surface, on the soft surface with our optical design. So we're trying to do a similar thing. We make a human pressing our gel set sensors on hemispherical shape, and with no surprise, this is what we can see. So we can see that it's a round contact area with lots of change of the shadings at different directions that shows the surface normal is different, and is according to the direction of the incoming light, this color also differs. But on the other hand, we also do another experiment, pressing the sensor on another object that is exactly of the same shape, but is made of a softer material. And this is the information we can see at this time. It's still a round contact area, but you can see the color is dimmer. So why? So directly speaking, so that means like the surface normal is much more flattened here. But what is really happening is that during the contact, not only the soft sensor is changing, is deforming, but the object is also deforming. And the more object deforms, the more changed it is of this contact surface. And with the help of this optical design of photometric stereo, we can precisely measure how much changes the geometry during this contact process. And what's more, we can make a precise numerical measurement about like exactly the extent of change and use that to estimate the hardness level of the objects. So here is exactly how we did that. We actually use deep neural network structure since it's so good at modeling this high-dimensional data. And we use a combination of CNN and RNN. So firstly, each frame in the video goes through the ECNN, which tells about like spatial information. Exactly is what is the contact geometry and the force in this current frame. And then the information goes through RNN, which measures how this information changes over time. And then we output a number that describes the hardness of the objects. So nothing happens during this process of touching the avocado. So we want to make sure that this human is successfully grasping the avocado and the avocado is not dropping from the fingertip. And as a human, we can do this very well. We know that whether we are giving a proper force or not, and if it's not, the object is dropping, we are automatically using a larger force to secure the grasp. How does this happen? So again, we are trying to measure the physical process happening on this contact surface. So specifically, we actually use the stake and the stake ratio to measure whether slip is likely to occur very soon or not really. So if the shear force is very small, like if we're squeezing really hard, your entire soft fingertip is actually stake on these objects. But if the gripping force is relatively smaller and this object is slowly moving away, so there is actually some areas on your fingertip that is not stake on the object anymore. And we as a human, we can measure this information and use that to tell us like whether this grasp is successful or not. So can we use Zhang to do a similar thing? So we do an experiment. We ask the robot to grasp something with a flat surface like this, and this is what the Zhang sensor measures. So on one hand, there's no specific information about geometry because everything is very flat, but we can still track the contact force, especially the shear force, by tracking the motion of the markers. And you can see that when the shear force is smaller, all the markers is moving towards one direction with a smaller distance, and when the force is larger, the markers is moving with a much larger distance. But on the other hand, actually, if we are considering the relative distribution of those markers, they also change as the force increases. Like when the force is very small, all the markers is moving very evenly with the same magnitude. But when the force is much larger, so actually the markers in the middle area is moving much further than markers in the peripheral area. Why? This is exactly the same mechanism as a human's fingertips, like stake and the slip area like. So when the slip is going to happen, there is some non-stake areas starting from the peripheral area of the contacts. So that's actually so as the same function as stretching our skin. Or if we want to make a numerical measurement, we can find that the displacement of the soft skin on the sensor in the middle area and peripheral area are different. So we can use this as a metrics to measure, like how likely your this object is staking your gripper, or how likely it's going to slide over very soon. So you may ask that, what happens if we're grasping some objects that has very rich textures and with a very small surface where we cannot track lots of markers within the contact area, like when we are trying to grasp this small doll. So what we can see is only this edge area and this small dot. So we cannot track the overall distribution of the markers, but we can still see what happens with the contact geometry. So here I'm taking a zoom in of these small areas, and we can see this as the change of the color tells us this is the edge of the contact of the objects. And after a little while, we take another look at these same areas. We can see this geometry actually has moved for several tens of pixels. So it's very small, but Zhang is very precise in measuring that, and that tells us this doll is slowly sliding down from the gripper. And that exactly matches the definition of slip. And we call this as translational slip case, where the grasp is going to fail. So in another case, if we're trying to grasp something that is thin and long, so we can still track how the geometry change, and by this time it's more likely this geometry will rotate instead of moving linearly. So we know that this is another kind of failure cases called rotational slip. So finally, we actually use this feedback to help robot to grasp. Like we ask the robot to grasp with a very small force, so that it's not damaging the objects. But if slip is or other kind of failure is detected, the robot will just regrasp the objects, but with a larger force. And with this mechanism, the robot can successfully grasp the objects in most of the cases. So. Of course, we did lots of other fun things, but those are some examples about how high-resolution tactile sensing can help robots for like fine details and general perception and manipulation tasks. So we learned that it's very beneficial for the robots to measure those fine geometries about the contact surface as well as the force. So it can help robots to recognize the materials, the objects, and understand state of physical properties. But on the other hand, if our goal is to measuring the fine geometry about the contacts, so currently the only solution is using optical design and vision-based sensor. But still, there's lots of existing challenges, so we're exploring and we're looking for more answers from you as well. So the first challenge is that how can we better model and simulate the sensor? So why do we want to do this? Because everyone in robotics wants to do simulation. We found that it's so important. It can help us to test whether a robot system works well before building the real robot. And it can also help us very easily collect a large-scale data set. So you know that in this new era, data is very important. But collecting robotics data is so expensive and so time-consuming. But simulation makes everything much, much easier. So unfortunately, there's no good solution of simulating tactile sensors. So we're trying to see what we can do. So my student, Arpit Agarwal, who is also sitting there, trying to simulating the structure of simulating the jaw size sensor based on the physical design of the sensor. So in other words, he tried to disassemble our sensor, look into like all these optical components, and model each optical components, and reassemble them in the simulation environment and see how those how these components will work together and form this image in this embedded camera. So specifically, he has been using this method called physical-based rendering. So it's a computer graphic method about trying to see what the render image is like by tracking the many flows of the light. So each time we sample a single ray of light, see how it bounces around in this environment until some of them reach the plane of the camera and post some change on 1 pixel in the camera image. So of course, like in this process, one of the biggest challenges is that how can we precisely characterize each optical components to make everything works well. But finally, we got some solution, and we reassemble everything in this physical simulation environment and try to simulate what the optical system is like in simulation. And this shows our results. We can simulate the readings of the sensors under different contact cases and the different geometry of the sensor surface. So at the same time, we also found this physical-based rendering is not only help with simulation, but it also helps us to answer lots of important questions in design. So for example, this is a sensor we recently got very interested in. So this is a round-shaped sensor designed by Ted Adelson student. So you can see that it has a round shape, which is very useful for robots, since with this sensor, the robot can detect contacts from different directions and can do some complicated manipulation tasks. But also, this round-shaped task, this round shape also makes it very challenging to design the optical systems. So the optics of this sensor is way, way more complicated than the traditional sensors. So we can still use that to measure the 3D geometry, but it's not working as well as the old sensor. Of course, there are always some design questions like what is the optimal shape of these shells of the sensors and the gel of the sensors? How shall we design this illumination system? Where shall we put the camera? How shall we choose the lens? So traditional, those questions are answered by trial and error, so which is a tedious process, takes enormous time, and it's almost impossible to get the best answer to that. But now we have simulation. We can play with different designs and change the components in simulation environment. So we are actually collaborating with Yannis and Heather Edelsons to figure out what is the best answer to those design questions. And Arpit is showing a poster of his recent progress here, so he will be more than happy to talk to you offline about like his recent findings. So another design question we found is interesting is a design for the soft robot hands. So the soft robot hands has a shape like this. So compared to the traditional rigid robots, it's made of soft materials entirely. So it has infinite degrees of freedom of motion. So my student actually make another robot finger that has a similar function as the one shown here. So it's driven by air. So when the air comes in, it will expand and bend in the directions we expect it to. So we're trying to make a tactile sensor for this finger as well. But you can imagine it's very challenging because the contact surface is large, but the entire area is small, while everything is moving during expanding. And it's very hard to design the optical part when everything is moving. So we try to do the same thing, like putting a camera in the back and design the illumination system. This time we use optical fibers so that it can make everything more compact. But again, there's a big challenge about like how can we design those illumination system? Where shall we put the cameras? How shall we choose the lens? So those questions will take like enormous time to answer if you're working with a real robot. But again, we try to work with simulation. We play with all those design factors in simulation and pick the best one and try to reproduce this design with a real robot. And this is our first prototype. How about like using this optimized design, which you can see that has a very weird shape of the optical fibers. And we try to make that for the robot, make the robot to grasp this fox lime, so the fingers that can actually see those fine textures on the lime as well. So another challenge we are facing is that how can we make the sensors more compact, especially if we're thinking about like if we want to make a skin for the robots, which cover a large area. So this is a beautiful system designed by Gordon Chen's group. So you can see that with this kind of requirement, we can now use lots of space. Like for example, the current gel side design, we will have these big cameras behind the camera, behind the sensor surface. That is almost impossible. So that requires us to take some smart designs to make the sensors more compact, or use some new designs optics to move the camera away. So the solution we are exploring now is using microwave guide to make a flexible tactile skin. So this is a collaboration work with Professor Misam Chimanzar, who is also sitting here. So we're using his technologies about making very, very small and thin waveguides on a soft base, so that we hope that it can cover the surface of the robot areas where move the optical signal far away for detection. So specifically, we are trying to use a microsecondary interferometer structure to detect the deformation of this soft skin, and make them into an array of the sensors so that it can measure the distribution of the contact. Okay, so that's reached the end of my talk. I would like to thank all my wonderful collaborators on making those things possible, and thank you for listening.
Great, thank you for this wonderful talk. We have time for a couple of questions.
Hi, that was really a great talk. Thank you. You must have thought about this, about using your gel site technology for making better fingerprint detectors. Have you thought of that? And can you say something about that?
Yes, that's also a very good question. So we think that is a very straightforward challenge for gel site, like for this particular, oops. Sorry, this video disappeared, but we can see the fingerprint so well. So we think that is not too much a technical challenge, but it's more like an engineering challenge and business challenge. So we haven't spent much time here, but I think technically it's totally possible.
Yeah, I think we could really use a better fingerprint detector. Thanks.
Thank you.
Another question? Go ahead.
Yeah. As you show that there's all kinds of different force, and apply on the materials and the different contact angle. And as you see that the gripping or the bonding depends on the contacting angles and also that surface chemistry and textile. So besides the optics and what's the other modalities or detection methods you are using to integrate to make it more close to like a human finger?
Thank you. That is a very interesting question. So human finger is, regarding to the sense of touch, is pretty like multimodals. We are measuring like lots of different information upon the contact area. So other than the mechanical change, such as like the static force or vibration and distribution of the force, we do measure also like the pain, sense of pain and temperature. We don't really have that at the moment. So our sensor is only at the mechanical level. It's only measuring the deformation. But we're also different than humans. It's like our resolution is actually far better than human fingertips. Like I think it's human fingertip has a spatial resolution about like 1 millimeter, but our sensor has a spatial resolution about like 25 micron. So it works a little bit different, but we still believe that we can get lots of inspiration about like how human fingers feel things.
And maybe one last question. My
question is regarding the applicability and maybe miniaturization of this sensing module. We talked about fingerprint because it's actually related. I mean, it's the same size of a finger, right? Both sensors, even though they use a different application. But still, you have fingerprint detector today that are optic-based on IR sensors, and you even have fingerprint based on ultrasound. Now, both of those things may be combined with such technology, and this may be a shortcut in order to get miniaturized model that you'll be able to place on larger surfaces.
Mm-hmm. Thanks very much for the suggestion. Yes, I totally agree. Like there's multiple ways we can detect the contact and detect fingerprint. So actually, this reminds me of some discussion I had with some like medical people. They're not specifically interested in detecting fingerprint, but they are more interested in like other state of the skin, such like the pulse or texture of the skin, or even some other physical properties like how smooth is the skin, how humid is the skin. So we can detect that as very well because like we can get dynamic measurement about like how this physical contact happens and how that will influence the readings from the sensor. So I do think like there's lots of more information. For example, if you you want to go beyond the geometry of the fingerprint, but also into like the state of the skin, like whether someone is nervous or not, and whether someone is in a good health condition or not. I think like sensors like gel sight can make a good complement to the system.
Yeah, maybe that future robot will also be our physician, right?
Yeah, there is already lots of interest in this field, and of course, everybody is welcome here to contribute to this topic as well, and I look forward to learn more from you.
Thank you.
I think we need to move on to the next speaker, so maybe the question can be taken offline, but let's thank our speaker again.
Hello, everyone. My name is Atul Ingle, and I'd like to welcome you to session 3 this morning. We have an exciting lineup of 4 speakers in this session. Just a quick reminder during Q&A, please walk over to the mic when you ask a question. That way our live stream audience can hear the questions too. And with that, let's get started with our first speaker, Yuval Harrell from Tel Aviv University. And he is going to tell us about a 2-level auto-encoder for distributed stereo coding.
That's right. Okay. Hello, everybody. Good morning. So I'm going to talk about my work I did under the supervision of Professor Shai Avidan in Tel Aviv University. Our work is a 2-level auto-encoder for distributed stereo coding. So let's break it down into. The first part is a 2-level auto-encoder. This is how we do it. The second is distributed stereo coding. This is what we do. Let's talk about what we do. In order to do it, let me please introduce you 3 schemes of compression. So the first one is single image coding. A single image goes through some encoder to compress the presentation, and through decoder to get the reconstruction. Second is joint coding. 2 images or more get compressed together, and you can leverage the correlation to further compress the image. This goes through a decoder, and you get a reconstruction. The third is distributed source coding. You still have 2 images to compress, but this time the images are distributed. They are transmitted independently. So you need to compress one of the images alone and decompress it with the help of the other. So distributed source coding first part looks like single image coding. A single image goes to the encoder without any other information. The second part, the decoder, have some more information that we can use. So distributed source coding, where can we find it in real life? So those are 3 examples. The first example is a camera array taking a picture of a certain scene. The second example is an unstructured camera array taking a picture of a certain scene. For example, when you're going to a rock concert, when everybody tries to upload about the same image to their social media account. That's the second one. The third is an image of an instance of something that has many instances on the server. So in all of these cases, the image that we are currently taking have a correlated image which is available at the computer or the server side, at the decoder side, but is not available for us during the taking. So now we understood distributed stereo coding, distributed coding. Now let's talk about our problem and what we are trying to solve. So our problem setting is the follows. We have stereo cameras, and we want to compress one of the images and decompress it with the help of the other. Okay, so at compression time, we have access to one of the image. At the decoder time, we have access to the compressed representation together with the other image. The previous work that tried to solve exactly this problem used a patch-based method in order to use Y to help with the decompression. One of the cons of this patch-based method is in order to do patch matching, you have to have some common information between the images. But that's a compression problem, and we want to send only X unique information and not the common information that is already available for us and Y. So I don't have time to go to all the pros and cons. If you want to read more, please see the paper. But I will say this. We tried to avoid a patch-based solution. We wanted to work on the entire image at once. And this leads me to our architecture. And let me tell you about how we solve the problem. So we start with a basic auto-encoder structure. And our contribution is a second-level auto-encoder for compression and use of the side information. So it's a big image. Let's break it down step by step. The first part, X go through E1 to WX, a feature representation of the image. Then it goes through E2 to get a compressed representation, ZX. So that's the encoder side. Let's move on to the decoder side. The decoder side, we have ZX and Y as inputs, and the output is the final reconstruction of X. But how does it work? Y goes through E1 to get WY, the combining feature space of Y. That's the same E1 that X went through at the beginning. Now ZX goes through PD2, partial decoder 2, to reconstruct the feature of X given Y, the unique feature of X that does not exist of the image in the image Y. Now we decode the two together at CD2, conditional decoding, taking the relevant information from the side information image Y, together with the unique information we have from X. That goes through D1, and then we get a final reconstruction. A few notes about the architecture. We work on the entire image at once over here, and we let the network learn the correlation between X and Y. Because we are talking about stereo cameras, we let the network learn the correlation between the two cameras, and that lets us send only X unique information and let the learning blocks have a lot of information about the geometry and other stuff in our system. Okay, so hope you made it so far and it was clear. Now we're moving on to the fun parts. Let's see some results. We worked on 2 datasets. The first is a Kitty Bay dataset of stereo road scenes car. About 1,600 images in this dataset. The second one is the Holopix 50K dataset, a bit more images, but it comes from a wide variety of scenes, not only road scenes. Generally, it had smaller disparity between the images because the pictures are taken from smartphones. So let's see our results. So on the top, you can see 2 non-deep methods at a compression point of about 0.04 bit per pixel. On the bottom left, you can see the previous patch-based method that uses side information at the decoder side at 0.04 bit per pixel. And at the right, you can see our method at 0.03 bit per pixel, which is a compression rate of about 1 to 700. As you can see, we achieved the best result over here. Let's see some more. That's a state-of-the-art single image compression method in a bit point of 0.05 bit per pixel. That's the previous work that uses side information at the decoder side at a bit rate of 0.05 bit per pixel. And this is our work in 0.03 bit per pixel. The lowest bits we send, and we still get the best reconstruction. So we did this calculation over the entire data set when we achieve those rate distortion curves. So let me tell you about the curves. The y-axis is the reconstruction score, MSSIM, the higher the better. The x-axis is the bit rate, amount of bits we send, bit per pixel. The lower, the harder the compression is. We can see our method, the blue line, is across all the lines over all the bit range. And the previous method that used information, the dotted orange line, a bit below us. We can see that our biggest gain is in the very low bitrate regime, which makes sense. And in the Holopix dataset, which the disparities are generally smaller, our method really excels. Okay, let's move on to one other example from the Holopix dataset. So this is the side information image that is available for us at the decoder side. That's the image that we want to compress. As I said, Holopix have generally smaller disparities, so we can see the image share a lot of common information. But still, we have some unique information that is only available in X and not available in Y. For example, the man's shoulder or the distance between the water glass and the menu. So what would you choose to send from the image X in order to capture both the unique information of X and the shifting of the existing information in Y? Anyway, that's the results that our system got in 0.03 bit per pixel. We can see that we're making pretty good use of the side information and keeping high frequency details together with unique information that was not available in Y. So with the question of what would you choose to send from X, let's move on to our ablation study. We did the ablation study when we took our system that were trained as follows with side information and tested it without side information. And that way we can see what our system sends when we have no side information available for us. So this is what we got. This is the image that we sent. And at the output, we get the following when we're not using side information. So as we can see, our method learns to send only the general shape and structure of the image, and all the fine details of text, of colors and texture are derived from the side information image. When we're using side information image, we're getting these results. Okay. One more thing we tested our system for is disparity estimation. So as you probably know, stereo images are commonly used for depth estimation. So we try to see if our reconstruction is good enough to do it. So we took the original pair of images, X and Y, and calculated the disparity map from those pairs. We took our reconstruction X set together with the image Y and calculate disparity from this pair and calculate the difference between them. We did this calculation over the entire Kitty dataset, and we got the following results. At our lowest bit point of 0.03 bit per pixel, about 1 to 700 compression, more than 50% of the pixel got accurate disparity results as the original pair. About 20% got 1 pixel shift of disparity, and the last column is for 5 pixel shifts or more. So to conclude, in our problem setting, at a compression ratio of 1 to 700, you can get a construction of high quality, a pretty good estimation of the disparity, and there is a pretty straightforward extension for our architecture to a bigger camera array. So think about it. You can add another 700 cameras at a communicational bandwidth of a single image. Our code is available. Thank you very much.
Thanks, Yuval. We'll take some questions from the audience now.
So you did the training on the Kitty data set, and then you evaluated on Kitty data set, or you evaluate across domain to the smartphone data set?
So we evaluate on the Kitty test set, and we try to evaluate also across domains. We still get pretty good results, but not as good as the one that trained this domain.
Okay, and
because the network really learns the geometry of the Kitty data set.
Okay, but I still guess it will work across domain as long as you are talking about stereo pair, where the difference between the images is, let's say, horizontal offset. Okay, thank you.
Hi, this was a really interesting talk. I just had a question about the architecture. Can you go back to that slide?
Yeah, sure.
Yeah, so my question is, why, like, what's the intuition behind E2? Because ultimately, you're using ZX, right? So why not just have one?
Why just combining them together?
Yeah.
That's the question? Yeah, thank you for the question. So I didn't say because I didn't have a lot of time to get to it, but in the training phase, we wanted to make sure that WX learn meaningful features. So we actually took WX and inserted it into D1 and penalized the loss for the reconstruction of WX. So during training, we also have a loss for the reconstruction based on the features of WX to make sure the features that are learning are representing the image very good.
Okay, yeah, that's pretty clever. So is there any significant architectural differences between E1 and E2, or it's the, like...
Our architecture is...
No, is there any significant difference between the architectures of E1 and E2, or they are very similar?
Very similar. Okay. It's all fully convolutional network, nothing fancy over here.
Oh, thank you so much.
Thank you.
All right, let's thank our speaker again. Our next speaker is Tianyi Zhang from Rice University, who will tell us about first arrival differential LiDAR.
Hello. Hi, everyone. Today, I'm presenting first arrival differential LiDAR. My name is Tianyi Zhang, and I'm a PhD student from the Rice Computational Imaging Group. This is a collaborative work with Molnar Group at Cornell University. So nowadays, 3D sensing has enabled a wide range of applications from augmented and virtual reality, autonomous driving, face recognition, etc. And many of these applications has become so available to us today thanks to the advances in 3D imaging technologies. And many of these can be accessible just right out of our pockets. For example, for those of you who have an iPhone, that's for the later model, you guys probably know that there is a 3D sensor, specifically a LiDAR, equipped on the phone. And it could allow us to do Face ID and allow developers to do a lot of fun applications, such as AR, VR. And iPhones are equipped with this specific kind of LiDAR called flash LiDARs. So the idea is to have a 2D array detector coupled with flood illumination. So that allows all pixels to be acquiring depth at the same time. So flash LiDARs are a very promising type of technology. First, it promises a future where we can have high spatial resolution depth maps, also at the high frame rate simultaneously. And many of the flash LiDARs that we see today are starting to use single photon avalanche diodes, or SPADs, which has great properties such as very high photon sensitivity, super sharp timing resolution, and also CMOS compatibility. And these systems tend to also be very compact, so very suitable for smaller devices. While there are all these promises, it's unfortunate because if you look at the sensor implementations today, they actually have very low spatial resolutions. For example, you'll be surprised to hear that the iPhone raw sensor resolution is only 24 by 24. So why does this issue persist? So to understand this issue, let's look at how flash LiDARs work. So on the top left is a flash LiDAR system. There is a pulse laser source coupled with a SPAD array detector. So this laser will be applying flood illumination to the scene and sends out a very narrow laser pulse repetitively. And for each period, the SPAD array will detect a time of flight for every photon that arrives. It's called photon time stamping process. So it's not hard to understand that the depth is basically the time of flight normalized by the speed of light. Many times, people accumulate these timestamp into transient so that it allows more robust and less noisy depth detections. But this process is highly expensive. The first problem is high data throughput because we need to timestamp every photon arrival. And to really encode the absolute time of flight and ensure good range and precision, we need many bits. For example, if we just choose like a not even very high pixel activity and with common operating parameters, for a 1 megapixel array, you'll get over terabits per second of data throughput from the timestamping. The second problem comes from the complexity of the circuit. So SPADs are typically coupled with what is called time-to-digital converters, or TDCs, to generate these quantized timestamps. And these circuitries are very bulky and power-hungry. And on top, people often even add on more complex circuitries like histogrammers, which even makes this problem worse. So we want to come up with a solution. We propose a solution to this problem. So the main problem is that we want to get, in these conventional designs, you're getting absolute timing all the time. So instead, we propose a first arrival differential LiDAR that exploits relative arrivals. So instead of sampling absolute depth at every location, now we look into, we devised a lightweight, what we call FAT unit, that samples dense and high resolution differentials across the whole array. And we combine them with sparse absolute depth references sampled with TDCs that are very sparse across the array and generate a high resolution depth map. One of the key insights we have is that we exploit the sparsity and spatial gradients of depth. And this is analogous to one of the very famous sensor works called gradient camera, which exploits sparsity and the intensity domain. And they try to do high dynamic range imaging with the construct. The key features are, first, a very low pixel pitch because the logic is very simple. And furthermore, this differential unit generates a single differential count per pixel that correlates with the depth difference. And so that removes the need for the timing dimension. And combined with the sparsity and gradients, we get a much lower data throughput. So let's try to understand how it works. So now imagine that we have a detector correlated with a laser source. And we have 2 pixels, SPAD1 and SPAD2. And let's say SPAD1 is looking at a point of the scene that's closer to the sensor, so it has shallower depth. Essentially, what the FAT measures comes to this question that over some integration time, how many times does SPAD1 gets an earlier arrival than SPAD2? Let's look at some examples. If SPAD1 is so close to SPAD2 in depth, then maybe 10 out of 5 times you'll get earlier arrivals in SPAD1, and 5 out of 10 you get from SPAD2. Let's say we make SPAD1 move, like the point move a little bit closer to the sensor. Then you might get 6 out of 10 instead from the SPAD1, etc. So if we increase the depth gap, you'll see more early arrivals from SPAD1. And if this gap is large enough, you'll almost always see SPAD1 arriving earlier. So notice that in this process is stochastic, but the probabilities of these events, intuition tells us these are monotonic. So in this paper, we derive the probabilistic model for this monotonic relationship. And we also, on the right side, we show the detailed logic layout for this operation, which is very compact. There is a set-reset latch for detecting the photon arrival orders, a counter for basically registering the differences, and an end to force both SPAD branches to fire in order to make a comparison. We also performed a back-of-envelope analysis of the chip area and throughput, which are very important for considering a high-resolution architecture. So first, we look at the data processing aspect, and we demonstrate how FAT can result in almost 2 orders of magnitude less data throughput compared to traditional TDC-based designs. From the circuit footprint aspect, because the logic is so simple, it results in a huge reduction in footprint compared to the TDC-based pixels. Now that we have the forward model and the circuit design, let's talk about how to use these FAT counts to do 3D applications. So first, of course, we have to acquire these differential counts by connecting adjacent pixel pairs in horizontal and vertical directions densely across the array. So that gives us the dense relative information. And next, we estimate the depth gradients from these counts, and we have inversion scheme for doing this, and that gets us the depth gradients. With these depth gradients, we can perform very simple processing in order to do some scene inferences already. For example, getting depth edges, segmentation, naive estimation of surface normals. And notice so far that we are only using the differential information. Now, let's talk about how to realize the FAT LiDAR idea, which is about getting high-resolution 3D maps, so everything is absolute. So we propose a segmentation-guided depth reconstruction. So here, first we have the segmentation and surface normals from the previous step. And we couple this with the absolute depth that are sampled using sparse TDCs. So the segmentation can allow us to parse the surface normals so that we can integrate each normal surface along each object. That gives us the relative surface per object. We align them with the absolute depth that are coarsely sampled to get back the high-resolution 3D maps for the entire scene. Now let's show some imaging results of this construct. So to evaluate the performance, we do this emulation process, which is scanning a single pixel MPE SPAD and obtaining individual photon time tags. And we simulate the differential logic on top of these photon time tags. And here we're showing what happens when we apply the 3D inference. And we can see that these produce some really decent features, such as the spatial gradients, surface normals, the edge mass, and segmentation. Here we show the 3D imaging and depth reconstruction results. So here we compare ours with the ground truth, which is collected by setting a very long integration time. And as you can see, ours has a pretty good quality that is almost comparable to the ground truth. So we also compared our idea with a few conventional TDC, conventional LiDAR baselines. So these baselines are chosen based on classic LiDAR architecture papers, and each of them sacrifices a different dimension of the imaging performance, including depth resolution, depth range, and spatial resolution, in order to maintain the same bandwidth as compared to our solution. So here, the comparison is bandwidth aware. So as you can see that under the same bandwidth constraints, our method could actually yield some advantages in the imaging performance. So yeah, we mentioned how flashlight imaging with flashlight arrays at high resolutions are hard, and we have a solution that exploits relative arrivals. And now I'm open, I guess. Yeah, check out our posters. It's close to the pool in the afternoon. Yeah.
Yeah,
thank you.
Thanks for the talk. Let's take some questions.
Yes.
Hi, I have a question regarding being an end user of these things. Can you talk a little bit about what is the form factor and the working range of your sensor? Like how small the integrated system is, and also can you make it work? Like for example, if the object to be like for the 3D application, if the object is, let's say, a centimeter away from the sensor itself.
So regarding form factor, you're talking about the size of the sensors that we're getting. So I think it could be scale to like higher resolution than the LiDAR designs, but I guess I don't have a very clear idea on that. Yeah, I guess I don't have a very clear idea of form factor, but I would expect like it will improve in many aspects like fill factors and allow smaller pixel pitches, but I can't like quantify the number. But in terms of ranges, I think like in our experiments where we carried out, it's around like meters of range. Because like we're doing dual rivals, we don't really expect, so it requires both spouts to fire. We don't expect it to work at very long ranges, but I think within like medium range, it can give us benefits in resolution, et cetera, and give us really useful features. Yeah.
Thank you.
We can take one more question. If not from the audience, I can ask the question. It's really interesting work. You mentioned important aspects for sensor design being data bandwidth and the amount of space that the pixel area itself. Did you think about power requirement for this sensor? Is it very power hungry, or does it save you power compared to, say, the sensor that's on the iPhone that you showed?
Yeah, I think, yeah, if we're going to high resolution, the traditional, I think our design, because it's so simple logic, so it will definitely give benefits in terms of power. Whereas TDCs, as I mentioned in the presentation, it will be like much more power hungry, and also the data reading process will also be power consuming as well.
Cool.
Yeah.
Thank you.
Thank you.
Great. If we don't have any other questions, let's thank our speaker again. And our next speaker is Bhargav from Rice University, and he'll tell us about a new method for single-shot 3D depth imaging.
Okay. Thank you, Session Chair. Hello, everyone. Today, I'm here to talk about single-shot 3D microscopy technique. And this is based on a new PSF, the Polarized Spiral PSF, or PS2F in short. And this PSF has been engineered to best image linear structures. So in microscopy settings, there are many scenes in which you would have 3D extended linear structures. For example, when you're imaging blood vasculature, when you're imaging neuronal vasculature, and maybe filaments in cells. All of these comprise of lines, edges, or curves, which are all locally linear structures, hence the name. And so traditionally, these have been imaged using scanning-based methods such as confocal or light sheet microscopy methods. There's a benefit in doing this in a snapshot 3D sensing fashion, so you can have a faster acquisition and potentially a compact acquisition system as well. To do so, the thing we can rely on is PSF engineering. So what you can do is you can add a mask in the pupil plane. This will modulate your PSFs, and these modulated PSFs can better encode your depth or give better depth discrimination ability. Now, this has been done over several different works. I have highlighted the ones that are done in 3D microscopy itself. And the main limitation of these engineered PSFs in microscopy was that they have been designed for estimating a sparse set of 3D point sources. So all these methods were used in conjunction with STORM or PALM, where you have a sparse set of photoactivations. And so it makes it ill-suited to image extended structures. For example, when we try to image a fluorescent strand seen in 3D, with conventional techniques such as confocal imaging, we could get a nice 3D reconstruction with about 100 images. If we try to do this with the DHPSF in a snapshot manner, we get a very poor reconstruction. In this work, with simple add-ons, we are able to get a much better reconstruction of such structures. And Yeah, so to explain this, let me get into the details of what the DHPSF is and why it is ill-suited to image lines. So this DHPSF, or double helix PSF, was one of the seminal works involving an engineered point spread function. Pavani and colleagues in 2009, they developed a phase mask based on rotating paraxial beam theory. And this phase mask created a PSF that has two lobes, and these two lobes rotated with defocus. So what you have is you'd have a PSF with two lobes, and each of these different depths would have different lobe orientations on the sensor. So if we try to use this to image, so here's an schematic of that. And so if we try to use this to image lines, let's say. So we'll start with a simple example. We consider a small line patch at a certain depth, Z. Then the image of this would be the line convolved with the PSF for that depth. So if you have a line at depth Z0, let's say a vertical line, you would convolve it with the PSF for that depth, and you'd see an image on the sensor which is something like this. Here's another example. Let's say if your PSF for that depth is vertical, you would just see the image on the sensor would be just a simple line. So from all these line patches, if we want to have unambiguous and precise depth recovery, we need all such line patches to be dissimilar or different. Now to do so, now here's where we run into problems with the DHPSF. So for example, if let's say we are imaging a vertical line, there are certain, so PSFs at slightly differing depths are all going to produce very similar line images. This happens at certain line orientations and certain line depths. And you can think of it as PSFs that are nearly symmetric with respect to the line are going to do so. So this, you can call this as local depth ambiguity or imprecision. And we have quantified this in terms of Fisher information and Kramer-Rauler bounds in our paper. This is not the only problem of ambiguity. We can also have a global ambiguity where if you have PSFs that are mirror images of each other, they're going to produce very similar line images. So now you have all sorts of depth ambiguities with the DHPSF, and this mainly occurs because there's some sort of a symmetry that's being imposed. So if you want to remove these ambiguities, you would have to break the PSF symmetry somehow. You can do this in many ways. Maybe you can do a multi-capture method, or you can even parallelize the multi-capture in different 4F channels. But if you want to do the most simplest solution is to just try to image these lobes individually. And so what do I mean by that? So instead of having a DHPSF, if you can have a two-channel PSF where you would have just the individual lobes, you would get a two-channel image of the line, and now you can unambiguously recover depth. This is what we do in our PS2F work, and we encode our DHPSF lobes in orthogonal polarization states. Let me go into showing you how we can implement this in a compact imaging setup now. So we come back to our simple 4F system with the DHPSF phase mask in the pupil plane. And on the sensor, we would see the PSF that is two lobes with with rotation as per the defocus. We make a key observation that if we block half of the mask, we're going to see only one of the lobe to feature. Similarly, let's say we block the other half, the left half. We are going to see only the other lobe of the DHPSF to feature. And now we can leverage this, that partitioning of the mask implies partitioning of the lobes. We can leverage this in a smart manner by just adding orthogonal polarizer halves in front of our pupil plane. And doing so will encode each of these lobes in orthogonal polarization states. Furthermore, if we replace our sensor with a polarization sensor and image using this, we would obtain in our individual polarization channels, like the 90 and the 0, we'd obtain the individual lobes, while in the 45 and 135, since they'll allow, both mask halves are going to allow light, you'll see the entire DHPSF. And so now this is the PS2F setup, and we are able to image individual lobes in a very compact setup. So now that I've introduced this, let me show you some simulation results and experiments that we performed with this new PSF. So we simulated some 3D vasculature scenes using the Vasquezin dataset. And here's an example of a scene. And I'm showing you the 0 and 90-degree channels as red and green over here for illustration purposes. And with computationally reconstruction, we can obtain the 3D vasculature quite accurately. Our reconstruction algorithm is a simple least squares optimization with regularizations. And in this, we assume that the light incoming from the scene is unpolarized. Furthermore, we compare with other PSFs, such as the DHPSF and the Fisher-optimized tetrapod PSF. And we compare them with two-shot captures. And we see that for simple vasculature complexity, we have about a 2x gain in depth error and about a 3x gain for highly complex scenes. Here's an example of a scene where I'm showing you the ground truth depth map and the 3 reconstructions. We can see that the PS2F produces sharper reconstructions and gives more accurate depth estimates. We further realized an experimental setup with a simple 4F imaging system. And in our pupil plane, we added simple, our fabricated phase mask. And on top of that, we added our polarizers. And in our experimental PSF captures, we can again see that in the 0 and 90-degree channels, we are able to obtain the individual DHPSF lobes. So with this, we started to image 3D skew planar targets. And here's an example of a concentric circle target. We can see that we are able to reconstruct locally linear structures for many depths and for many different angles as well. Here is an example of, here are a few more examples of such 3D skew planar targets. I'm showing you the depth maps over there. Furthermore, we created a 3D fluorescent cotton strand scene. These strands were of thicknesses from 10 to 30 microns. And we can see that our method PS2F compared to the DHPSF gives a much sharper reconstruction, especially in the complex scene regions, such as shown in the zoom in inset. If we compare this with confocal ground truth, we see that PS2F reconstructions resemble much closely than the DHPSF. In fact, if we also look at the depth maps, we see that we have a much more accurate depth map than the DHPSF. So in summary, we analyzed what it takes to image lines and looked at depth ambiguities. And using that, we introduced a new polarized spiral PSF that was created using a polarization phase mask encoding. And this was capable of performing 3D sensing of linear structures. And moreover, you can construct this with simple add-ons on top of an existing DHPSF imaging system. I'd like to end this by thanking our funding sources and saying that this polarization phase mask encoding is an exciting avenue, and maybe you can do much more than 3D sensing and also do analyzation of polarization with this. Thank you.
So in one of your first slides, I think it was the third slide on the presentation, you had shown a comparison of confocal versus just DHPSF versus your method. Could you go back to that slide for a minute? So in this case, it seems like along the depth dimension, you still have some smearing of the reconstruction. That, I guess, doesn't show up in the depth map because you have projected it across the sea. Is it that you still need to improve your PSFs better to get that to work?
So that's a good question. So what you have is, we are still diffraction limited in this case, and in diffraction theory, you can see that your lateral resolution can be quite small, but your axial resolutions are large. So that's why we see in our reconstructions there's a spread in your axial domain. But overall, yes, I feel like maybe you can use better techniques, like maybe use learning-based mechanisms, or even use maybe likelihood schemes have been used when you're estimating point sources. Maybe you could use that to have better, like this axial resolution be better.
Hi, great talk. I just have a question. So it seems like a lot of the acquisition time in your method is transferred into the reconstruction time. So for a scene displayed in this size, how long would it take to reconstruct?
For a scene, so we have done this using, right now we have done our reconstruction using a simple optimization technique, and we have implemented this in PyTorch. So right now we take about an order of a minute to get this, but we can do much faster if we start doing patch-based processing and parallelizing it, or just start learning networks to reconstruct it faster.
Thank you.
Yeah, thank you. Very good talk. So I have two questions. First question is, I want to confirm, what is the working range in Z depths for a PSF?
Yes, so that's a good question. So we have so you can design your DHPSF for different depth ranges, and you can. So I've seen. So if you consider it compared to the axial airy disk axial resolution limit, you can possibly design your depth ranges to be roughly maybe 2 to 20 times your that value. So it's within a limited depth range that we are doing this.
Okay, cool. So the second question will be, I think like at the first you mentioned that this could improve the spatial resolution, right? So or improve the the density, you could not limited to imaging some sparse sample. So the inclination behind this is you only use half of the double helix PSF, right? So which means that you can imagine maybe double densities compared with double dense sample compared with the previous one, right?
So that's a good question. So we looked briefly at seeing a few bead reconstructions as well with this. It's in our paper actually, and we see that with higher densities of beads, we can get slightly better reconstructions than the DHPSF. However, we've not used likelihood-based methods or the state-of-the-art methods to do so. We've used our optimization algorithm to do so. So I'm not sure if this can be translated to use for bead reconstructions in very high dense scenes, and especially because you're also going to get light loss due to your polarizers. So, but it's an interesting question.
Yeah, so basically, for now, the density we could use for such task will be also storm, right? Storm application.
So here we are trying to move away from storm and say that we are trying to image extended scenes. So we are not really photon limited, and so that's why. Yeah, so we are not trying to use it in a storm-like setting.
Okay, thank you.
Let's take one last quick question.
Thank you, Bhargav, for the great talk. You're using 0 and 90-degree polarizers on the aperture mask, and I believe the sensor actually measures 0, 45, 90, and 135. You're kind of losing half of the light. So does it make sense to put all 4 masks, 0, 45, 90, and 135 polarization mask at the aperture instead of 0 and 90?
Okay, yeah, that's a another good question. So what if you add, the benefit of adding those masks is kind of unclear to me, especially I don't know if you could get this clean separation of lobes if we add in those 4 quadrant masks. But using this paraxial rotating beam theory, maybe if you can design 4 lobe rotating PSFs, and maybe if you add those 4 masks, 4 polarizers there, and maybe that would be a better encoding scheme as well. Here we try to do just minimal changes and come up with the simplest possible solution.
That sounds good. Thank you.
All right, let's thank our speaker again. Our next speaker is William Kruska from Boston University, and he will be telling us about a new non-line of sight doorway camera.
All right, thank you. 1 second. All right, good morning. My name is William Kurska. I'm an undergrad at Boston University, and today we're going to be exploring the doorway camera. Now, many of you may be familiar with the corner camera and its ability to resolve angular information. Well, corners don't often come alone, and so we want to explore how we could reconstruct a hidden scene using the doorway that leads to it and form a reconstruction in 2 dimensions. Now, this was first explored by Baumann et al., and although they mostly focused on the single corner camera, they also applied 2 corner cameras to a doorway, as we are going to, and by combining and manually tracing the 2 one-dimensional reconstructions, they were able to triangulate the location of an object in 2-dimensional space. However, this approach had a couple of limitations. Take, for instance, a hidden scene with 2 similarly colored objects. While they both leave distinct angular information on our measurement area, you can see that with the angular information alone, there's actually 4 objects that could conceivably satisfy those angles. However, we know that there can only be one unique solution, and therefore these 2 phantom objects must be disallowed by some mismatch. To address this, we look at the work by Seidel et al. They performed a 2-dimensional reconstruction with a single edge, and they used the azimuthal information again. However, they also utilized the radial fall-off patterns to get the range information. However, this approach is also limited in the fact that it has a weak performance with low SNR, and therefore it's not well applicable to real-world scenarios. Therefore, we are looking to build off of these 2 approaches and to reconstruct the 2-dimensional location of multiple moving objects in a hidden scene. To do so, we have developed a light propagation model for a pair of edges and a pair of background subtracted measurements. With these measurements, we are going to apply an inversion algorithm to jointly estimate the 2 views or reconstructions of the scenery in motion on a novel 2-dimensional reconstruction grid. And finally, we'll show you how this all played out with a variety of examples. Before we get too into it, we want to just review the mechanics of a quarter camera, as was used by a variety of folks. If we have a hidden scene with an object in it, there will be light reflected off that object onto the ground just outside of the doorway. If we measure the angle between the doorway and this object, you can see that at shallower angles, less of the object is exposed onto the ground, and thus there is less incident light. This pattern is called the penumbra. And if we apply this to the other corner of our doorway, we are now able to describe a single point in 2D space by 2 angles. Additionally, for each measurement area, there is a decrease in brightness as you get further away from the object called radial falloff, as it was exploited by Seidel et al. And we have also included this into our forward model. Now, before we attempted to reconstruct anything, we first wanted to understand the merits and challenges of our approach. And to do so, we derived the Kramer-Rao bound for a point target at alpha 1, alpha 2, and a height of 0. In a scene with no edge occluders and a single measurement, the spatial ambiguity was very high, and as we know, adding a single edge occluder greatly reduces the angular uncertainty. However, range uncertainty is still largely unaddressed. If we then add our second edge camera, we greatly reduce the angular and range uncertainty. I just want to quickly note that the uncertainty does still increase with distance. It's just too small to display here. Therefore, to form our reconstructions, we have to discretize our hidden scene. To do so, we split up the hidden scene into equiangular wedges emanating from each corner, since that is the strong suit of a corner camera. At the intersection of each of these wedges, we place a vertical facet. And if we do this for all of the intersections, we receive our reconstruction grid as seen on the right. For each facet, we are going to reconstruct 5 quantities. First, we're going to find the color of it, the red, green, and blue values of our facet. However, we would expect the brightnesses to be slightly different for each corner due to an angle or lighting change. And therefore, we have included the C left and C right. And if we multiply that against our color triplet, we have a unique color triplet describing a single facet from the left and from the right. We also break up our reconstruction grid into foreground facets, which are constrained to be positive value to describe objects that have entered our scene, as well as the far field facets for things that may have been occluded when those objects entered the scene and are therefore allowed to be negative. We can now describe the measurements we take of the corners. This is for one of the 3 color channels. First, with any change in ambient light that may have occurred between frames. With our light propagation model, as it applies to the 2 color triplets. And finally, any noise or mismatch. To solve for the 2 views as described before, we are going to minimize the above expression. This consists of the data fidelity term and of a group sparsity regularizer. We are performing group sparsity on the left and right luminance multipliers, C left and C right, and we minimize the expression through projected gradient methods. At the end of all that, we have our left and right reconstructions. However, it's often desirable to have a single presentable view. And so for each facet in our hidden scene from both, we find facets that are above a certain cutoff threshold for the left and right. And then those are the ones we include in our quote-unquote unified reconstruction. All right, let's see how it formed. We're going to start with a more drawn-out example to kind of paint the scene. This is synthetic data, and we'll move on to experimental data. So if we have a hidden scene, and this is a line-of-sight image from the corner for the left and the right, we have an accumulated background, and then we take a new frame where the objects have entered. If we subtract the background from this new frame, we can see we have added red and blue light. However, we have also occluded a significant amount of light. For the scene, the penumbral patterns on the outside of the doorway are as such, and if we subtract the background that we had accumulated previously and amplify the colors for viewing, this is the measurement we are ultimately going to form our reconstruction from. Our left and right reconstructions are as follows, and I'd like to point out that the luminance differences represented in the left and right reconstructions match the positive difference line of sight image shown on the left. The same applies for the negative portion of our reconstruction, and if we pull them together in our unified reconstruction, you can see that is very close in color and location to the ground truth of this hidden scene. So let's move on to a slightly more difficult example with 4 objects. Again, we have our penumbral patterns, and if we subtract the background, we're able to reconstruct their locations and their colors in 2-dimensional space with a good degree of accuracy. I then wanted to return to the problem scenario I had presented earlier with similar colored objects in a room. You can see, even with amplified colors, it's much more difficult to figure out exactly where an object would be. However, because we have included the radial fall-off patterns in the range data from it, we are able to reconstruct their locations correctly. We also performed a variety of other tests with respect to image degradation, such as lower resolutions and with decreasing signal-to-noise ratio. And we found that our method was robust to these as well as other perturbations, which you can see in our supplementary material. Now, moving on to the experimental results, we have a light source placed up high to light everything in our scene, a camera just outside the doorway taking a photograph of the floor, walls making the doorway itself, and a hidden scene just beyond it. And finally, we have our measurement areas on the ground, which are being photographed. For our first scene, we placed 2 mannequins in the middle of our room, and by the same method, we were able to reconstruct its location, and as well as the color. Now, moving on, we took these mannequins and pushed them to the back wall of the room. You can see that the signal we are working with is much weaker than the previous example. However, we're still able to reconstruct the location of these 2 objects, albeit with a little less accuracy on the color. And finally, we added one last object, and by the same method, we were able to reconstruct the location of these 3 objects in our hidden scene. So, in summary, we have developed a method to recover a 2-dimensional reconstruction of a moving hidden scene that is robust to low signal-to-noise ratio. And we have numerical experimental demonstration of this method working, as well as a point target analysis to show the merits and challenges of our method. Thank you. I'll just also add, we'll have a poster outside, so if you want to talk more about it, you're welcome to join.
Okay, great talk. We have time for a few questions.
Hi, very nice talk. I noticed that all your examples were with symmetric objects. I mean, you know, not asymmetric. And it's amazing how many symmetric objects there are in the world. So it really has a lot of, but I was just wondering if you had thought about asymmetric objects that didn't
Such
have
as
yeah.
an object that is like, taller on one side and shorter on the other?
Yeah, and perhaps no axis of symmetry, so how that would impact your shadows.
Yeah, so that is, to an extent, that is what we tried to address with the luminance factors for the left and the right, because we'd expect a weaker signal from one side of the object to the other. And so that would allow us to more properly explain it. And ultimately, because it is a 2-dimensional reconstruction, we're just looking at basically the projection of the rays of light. I hope that touches on it.
Yeah, no, that's great. And using your simulations, you could actually see what kinds of shapes it might fail with. Might be interesting. Thanks.
Okay. Any other audience questions? Otherwise, I have a quick question or two.
Go ahead.
Did you try adding ambient light on the measurement side where the camera was looking?
We did, yes, and it was not shown very well in the experimental results, but there was ambient light. But I didn't make a concerted effort to drastically change it between frames, and so it was largely accounted for.
Cool. Okay. And then how long does it take to reconstruct one of these images?
So it obviously depends a lot on the resolution we chose. It takes on the order of minutes because we didn't put a ton of effort into optimizing our code. But especially if we put it onto a GPU, we expect it to be a lot faster.
Cool.
Yeah.
One more question.
Hi, nice talk.
Thank you.
Oh, that's loud. Have you thought about if you're imaging like a dynamic scene, if you have something like moving, how you might be able to sort of leverage the fact that stuff is moving, like put motion consistency, would that make it any easier, make the problem work any better?
To an extent, we are sort of leveraging the motion of an object because we assume we are able to collect accumulated background, and so in that aspect, we're utilizing the motion. However, if you're talking about where the overlap is not a full object's width, and so there's going to be a negative portion object positive, we didn't quite consider that. But that would be an interesting avenue to consider.
Do you think it would make the problem? Do you think it would make the problem work any better? Not that, I mean, it works great now, but would it be easier or harder if you added sort of if the objects were moving and you tried to recover their path or something like that?
I think we would be able to incorporate that as maybe like a prior, like our previous reconstruction, and to influence the next frame. I haven't given it a fantastic amount of thought, but that's a very interesting proposition.
Cool, thanks.
Thank you.
Okay, I just want to end with a fun question for the fun camera.
Okay.
When will I get this fun camera on my smartphone? If you want to just put a number on how many years it might take.
The iPhone 37.
37, okay, cool. Let's thank our speaker again.
I think this is the, connect that. I just
switching out the adapter.
Perfect. And then there's a water right here if you need. Okay. Got it? Other way.
Oh, I think
this way.
it goes here, yeah.
Okay.
Oh, yes. What? Okay, good. Right.
Wonderful. Okay, great. Thank you. Let's wait for that.
I just like, okay.
All right, wonderful. All right, thank you everyone for being here. So it's our great pleasure to have, for our next invited talk, Professor Zhang Miao. John is a professor of physics and astronomy and the California Nanosystems Institute at UCLA. He's a world-renowned researcher in the development of imaging methods for X-rays and electrons, and has made a number of fundamental advancements in areas such as X-ray crystallography and electron tomography. He holds a number of honors and awards, including but not limited to, the Alfred P. Sloan Research Fellowship, Microscopy Today Innovation Award, and an NSF Creativity Award. So we're really excited to hear more about his work on computational microscopy. So please help me in welcoming Professor Zhang Miao.
Thank you, Oscar. Good. Yeah. First of all, I want to thank the organizer for inviting me to give the talk, and especially Katie. Katie and I have the one thing in common. That is, I'm not a typical physicist. She's not a typical engineer. I know most of you are from the engineering community. I assume many of you want to be rich and famous. I have a different goal. I once asked myself, you have one life to live. What will make you truly happy? Well, I said, John, money comes and goes, right? Money comes and goes. Fame comes and goes. But I want to do something that, see something nobody has seen before. This is a Hawking imaging field. And I want to make a discovery that can have a long-term impact. So with that, I'm going to talk about computational microscopy, coherent diffraction imaging with photons and electrons. Now, I believe there are revolutions. I try to, why it's not, okay, I just go this way. I think there's a revolution in the microscopy imaging in the diffraction field. Now, when we were in high school, we usually turn the knob, optical microscope, we can magnify the images, right? That's typically 100, 200 nanometers. Now, with super resolution fluorescent microscopy, you can get tens of nanometers, and CDI, again, top coherent diffraction imaging. Electron microscopy, near atomic resolution, and X-ray crystallography at the sub-angstrom level. But there's also time domain from minute to attosecond. Attosecond, one attosecond, 10 to minus 18 seconds. Light travels about 3 angstrom, about 1 atom size for 1 attosecond. The reason I believe there are revolutions is because brilliant X-ray sources such as X-ray free electron lasers is billions of dollars each. And also the advanced synchrotrons, that's almost $500 million, more than $500 million. Aberration corrected electron microscopy, and a powerful imaging method. As I mentioned, many of you are familiar, super resolution fluorescent microscopy, cryo-EM, and CDI. And also detectors made a very important role for imaging field. I mean, the detector actually originally, I visited the CERN, there's a high-energy physics lab. Okay, it's a very famous lab. It discovered, they call it God particle, Higgs boson. And they originally developed the detector because they want to count all the particles. And then they migrate to the X-ray field, electron field, and play a very, very important role with single photon electron counting, advanced algorithm, big data, fast computer, and deep learning. So this, I think, is the perfect way for this field. Now, I'm going to talk about the CDI. So let me just take one step back. CDI is it's a lensless imaging. So lens-based microscopy was first invented in the 17th century. Now, Robert Hooke, he was not the first one to invent a microscope, but he was the first one using light microscope to look at biological samples. He looked at a piece of cork, and he found these compartments. So he called these cells. So the terminology cell was first adopted by a physicist. And since 17th century, this lens-based microscopy, such as optical, phase contrast, fluorescence, confocal, super resolution, electron microscopy, has played an important role in the evolution of modern science. I mean, this is so important, so many fields, right? So everyone knows the lens actually do the Fourier transform. That's very familiar, right? Now, when the Fourier transform, the phase information is conserved, but when you the phase information is very important. One of my students did this, did a very simple computation experiment. She took 2 images, okay, 255 by 255, with a grayscale from 0 to 255. And then she calculated the Fourier transform of this image, get magnitude and the phase, okay? And magnitude phase, she swapped the phase and do inverse Fourier transform. You can see this actually looks like a B because phase information from B. This looks like A because phase information from A. So your eyes and my eyes are more sensitive to the phase information. Now, unfortunately, phase information couldn't be measured. Now, I'm going to do a demonstration here. I hope this will work. I use my laser point, and this is my cell phone. Okay, I just shine a laser on my cell phone. I don't know whether you can get some scattering pattern. Well, I tried some other spot at the work, so let me just try it here. So hopefully, okay, you can see that a scanning part. My hands are shaking because I had too much coffee. So when I scan the surface, this pattern is different. Okay, it's not because shaking. The surface is different because that's a pattern corresponds to Fourier transform in surface structures. Now assume you have X-rays, you can see all the atoms on surface, but our eyes cannot see from that pattern. Cannot get a surface because the phase information is lost. The phase information cannot be measured by detectors. So there's a way, there are ways to solve phase problem like holography, right? Dirac and Massey both got a Nobel Prize. And so I'm going to tell you a method called oversampling to solve the phase problem. Wait, why the information is, I don't understand why it suddenly disappeared, everything. It's on my computers here. So I have a question. It's just disappeared. I don't know why. On the screen. Sorry for that complication. You know, maybe just use this one. Yeah, this just, sorry.
You can do both.
Sorry for the complication. So I'm going to talk about oversampling. Okay, actually from the diffraction measure the pattern, we can get the phase. It's a computation method. It's computation algorithms. Is it okay? Oh, just restart my computer. Why is suddenly?
Here, hold on. There we go.
Okay, this is fine. Okay, good. Thank you. So, to understand oversample, let's first look at Shannon sample. Everyone knows Shannon. Shannon plays such an important role in our new era. Everybody uses Shannon sampling theorem, right? He's a father. He's considered father and a founder of the information and communication era. So when he was at the Bell Lab in 1940s, he was thinking how to send a signal from one place to another, from Los Angeles to New York. Digital signal. He was thinking digital signal at that time, 1950s or 40s. Now everybody uses digital signal, the emails. So before him, everybody used analog signals. And so let's have a signal, okay, this is confined to time t, is t with time with length a. You can take a Fourier transform engineering and you can get this wave. You can either send this signal or digitize this signal or send this wave, digitize. So he showed mathematically you just need to send these points. And people over there can exactly get a signal back. Now this is counterintuitive, but in physics, this is just an uncertain principle. The delta x times actually delta p, the momentum, should be larger than h bar over 2, the constant. So this from this point, I mean, right now, all the information, this email, the message received, if you measure they just send this information. But here, assume the phase information to know, right? Without the phase information, then you cannot use the inverse Fourier transform and get the signal back. So this is a big problem. And it turns out, if you only sampled 1 over A, this is called a Nyquist interval, you have an infinite number of the signal corresponding to the same intensity distribution. That makes sense, right? In any phase, combine this magnitude, the inverse Fourier transform, get different signals. But if you sampled the diffraction pattern finite enough, so you measure intensity at this point, at the Nyquist interval, but also between. So mathematically, we showed if you measure independent measurement, it's more than the number of unknown variables. So this paper actually, at that time I was a graduate student, I realized this becomes somehow just like a linear equation. It's a linear case. This is actually nonlinear problem. But somehow, if the number of let's have no noise, with the number of the independent measurement is more than the unknown variable of the signal, the phase information can be recovered by iterative algorithms. So you may ask, experiment, how can I do it? So let's assume this is actually a cancer cell, okay? You shine a coherent wave, you get an interference pattern, right? Let's assume you use n by n CCD to measure diffraction pattern. And each pixel size is 20 by 20 microns. So if you can get a phase information, you can get it back. But let's assume you do the same measurement, but here use 2n by 2n detector, same size. The pixel size is 10 by 10 microns. The detector size is the same. So if you do inverse Fourier transform, you get this back. Because the spatial resolution is the same. Everybody familiar, what? The spatial resolution related to the diffraction angle. So you get n by n, here's n by n. But this is 2n by 2n. And mathematically, one can show if you can get a correct phase information, this region must be zeros. It turns out that zeros in the phase. And so I'm going to show you this kind of iteration. So this actually experiment I did at the Brookhaven National Lab when I was a graduate student. This is an interference pattern from this ABCDEF, a bunch of gold dots, and each dot is about 70 to 80 nanometers. And from this interference pattern, actually we use iterative algorithm found. Now in the 1990s, the job market for physicists is horrible. I mean, just no job. I was thinking to go to Wall Street, because at that time, a lot of physicists and computer scientists and mathematicians, after get a PhD, go to Wall Street, earn a lot of money. And there's almost no job academia. But fortunately, I did this. The experiment was much better than expected. And so I can stay here to talk to you. And so here you can see you can see, right, this diffraction pattern. Just I showed the pattern I getting from the surface of my cell phone. And from this, you can iterate. If you do oversampling, sample is sufficient fine, and you can get the phase back, get the image. Now, this is not holography because the resolution in this case is determined by diffraction angle. Holography is determined by the reference beam, size of the reference beam, right, or the detector size. And so there's a lot of advantages. And a few years ago, my collaborator and I wrote a review article of science. So there's a lot of applications, and both for X-rays, light microscope, electron microscope, and so the tychography also can scan CDR is a very popular version. I think Professor Chang Wei Young will also talk about this. He talked about the Fourier tychography. So there's all this. Just basically measure diffraction pattern. Here use overlap. Overlap also increase the number of the measurements, reduce maintain the same unknown variables. So that's basically the principle. It's become somehow like a linear problem. It's amazing. And applied mathematics is also very interesting in this field. There are a lot of papers actually show how under what conditions this can be uniquely solved. So the problem is basically solved. Okay, so now just what kind of applications. So I'm going to show a few applications and a few new methodology development. One is, this is not my work. Okay, the only piece of the slide, the only slide that's not my work in this my talk. So the high-resolution 3D image of integrated circuits. Everybody know integrated circuits in the crisis, especially competition, the U.S., China, and so this work actually they use X-ray tychography. You can get a 15 nanometer 3D resolution. So the features getting smaller and smaller, from 9 nanometers, 5 nanometers, 3 nanometers. But how to see the defects? Current technology, you have to slice it, cut it, and yes, and SEM, TM to look at it. That's very destructive, slow. But ideally, you want to look at it non-invasive, non-destructive 3D, right? So this actually can see all the features, the integrated circuit. As a DARPA, actually very interested in this. We put a lot of money in this field. And also, now my group, we actually recently developed this called imaging the 3D magnetic vector field. Now, the magnetic material is very important. Your cell phone, these are all magnetic materials. So we use left and right circular light, and shine on the sample, and we use the soft X-rays. You can see with the left and the right circular polarized light, the contrast is different, okay? And we look at a structure made of nickel embedded with silicon dioxide. Silicon dioxide is not a magnetic material, but nickel is a ferromagnetic materials. So I'm going to show a movie. I mean, you don't need detail. This is a scalar reconstruction of the nickel, and the empty region of silicon nitride is silicon dioxide, low resolution RC. So here you see the vectors. We're going to zoom in, look at individual vectors. The resolution is about 10 nanometers, so about 5 nanometers per pixel, per voxels. So we look at, we find that there's some vectors is the topological protected, and you can see you'll see red corresponds, we call it topological monopole, and this is positive and negative. And we can then look at two positive topological magnetic monopoles. And so you can see this actually quantized. The topological charge is +1 and +1. And the line corresponds to magnetic field line, okay? So this is not a real magnetic monopole, but the topological magnetic monopole. Okay, this is actually theoretically predicted it can exist. And we also look at the two negative charge, so topological charge -1, -1. So that's kind of another, there's a lot of applications and also in biological science, but I just show it because of a time limitation. In the following, I'm going to talk about the methodology. Now, in the previous talk, they talk about how to get a 3D structure information from single view. Actually, in 2010, we published a paper in Nature, and we call it ankylography. Ankylous means curved. So now this is very interesting. Your eyes, I stand here, I can see, okay, Katie sees in the first row, and the second row, how many people? Your eyes can tell, give you Z-dimension information, right? Otherwise, how can you drive? And now another interesting thing, your ear, 2 ears, it's larger than the 2 eyes. Anybody know why? Well, that's because of sound wave. The wavelength is longer. So in order to get a 3-dimensional information, you have to further apart. I think that's actually makes sense. The 2 ears, actually, as far as possible in your head. Also have to make it symmetrical, right? So because of the curvature, they give the Z-dimensional information. The Z-dimensional information corresponds to this thickness, right? And we did the simulations, and it works fine. And then we did actually some experiment to use high harmonic generation, use wavelengths about a few nanometers. And we detect and measure this, but the spherical, the fact scatter wave is the scatter wave is spherical. So we map onto from a plane to a spherical wave, and then we did a 3D reconstruction. Now we have to apply some constraints because the information you measured here has to be more than the information you try to reconstruct. You cannot get something from nothing. You have to get something from something. The measured point, so you have to do further oversampling. And then we can reconstruct the sticker figure, actually this sample tilted by 5.1 degrees, we actually from our measure. This is Z-axis. We can see the Z directions. Now, after we published the paper, the community, CDI community, the actual community was, people said it's just not possible. It's not. If you look at our paper, there are even some 2 comments, and you load. But at the end, I think science is better than politics because truth prevails, right? It's not like politics. The loudest voice win. So we put everything online. So everybody interested, we put code everything online. So, okay, another technique, I thought this community would be interesting because we developed sort of broadband CDI. We can truly broadband. I think now wide beam is the delta E over E is about 50%. Okay, so we actually tried this attosecond pulse. The attosecond pulse, because of delta T becomes so short. The delta E times delta T, on certain principle, had very broad, 100%. So that's much broader than wide beam. Okay. So we did a simulation, measure the diffraction pattern scan with overlap, larger redundancy. You can see the diffraction pattern is very fuzzy because of the very broad band. And from this pattern, we can reconstruct, and it's amazing, we can reconstruct the spectrum and also the probe as well as the images. We did 17. So this, the red corresponds to true spectrum. This is a simulation on the test sample, okay? And then the green corresponds to covered the spectrum. Each dot corresponds, each wavelength we can reconstruct from just single direction. And this is a test, and this is one diffraction pattern. You can see very kind of fuzzy. And then we did it even with absorption edge, okay? With a boron structure, with absorption edge, we also get this. This is reconstructed spectrum. And then we did LED experiment. LED experiment, LED is a delta E over is about 50%, okay, lower than this. But this is actually, the red corresponds measured spectrum, green color recovered from our algorithm. Just a direct measurement. And so here shows our kind of a test simulations. You can see we actually show 3 different wavelengths. Okay, this is original structures. And you can see the field of view increased because the setup is the same. So this resolution is getting higher because the shorter wavelengths. The same setup, the resolution actually getting better, and the probe you can see actually getting larger. This is the reconstructed probe. This is the simulation, okay? And then we did this actually, there's absorption edge. There's Ato and CDI, different material. It's aluminum and it's boron. Boron has absorption at 6. It's suddenly at 6.6 nanometers, it suddenly jump up. You can show it again. So at 6.6 nanometers, and it suddenly showed up. So this is all from single, just one angle, one measurement. Okay, you measure a few patterns, but you all measured all the broadband. And then we did experiments, LED, and on the test sample, and this is a reconstructed probe, and you can see the different wavelengths getting shorter and the probe getting larger, right? And if you zoom in, you can structure actually quite good. I mean, of course, the resolution limited by the diffraction angle, diffraction angle, and the wavelength, and the spectrum also quite well reconstructed. So, so far I actually talk about CDI. This is why I briefly chatted with Katie yesterday. Now, we like to explore different fields. I mean, I found that everybody like to stay in a comfortable zone, right? Because you see your friends, chat. You don't like it uncomfortable because you go to new I actually come to this conference. I see some friends actually. Lola is my friend, and she's out here. And my former student also was here. But most of the time, we are like a comfortable zone. But I found, if you can get used to be uncomfortable. Comfortable is uncomfortable. That will have a big impact. Now, everybody knows the minimum optimization field, right? You can stuck in the local minimum. If it's comfortable, always local minimum. But if you go uncomfortable, then you can get a global minimum. And so we applied, actually, this CDI algorithm to electron microscopy, really solve some problem. We can see individual atoms 3D. I mean, we saw, this is all from my group's work. I mean, it's amazing. Now, this seems like a lot of people advertise for a postdoc. I also have a position opening. If you come to my group, okay, I cannot guarantee you will be famous and rich, but I can guarantee you can publish some important work. So because we focus on the important work, and you can see, and so especially I'm very proud that recently we actually solved a really essential order problem. The structure of the crystal solved in 1913 by Black's father and son. And the first structure solved the salt, table salt, and a diamond. And for more than 100 years, this amorphous material, this is metal glass, was first invented at Caltech. But nobody sees 3D structures. It's difficult. You want to get, we got a signal noise from single atom. Okay, it's not from single eye or single pixel from human, single atom. It's small. How can get all the amorphous? But actually, we solve is powerful computation algorithm. I'm going to show you. This consists of 8 different elements. Okay, we divide in 3 different colors based on Z, and the green corresponds low Z, medium Z, blue, and red is high Z. So I can see. And we found they're actually amorphous. You can see this is actually disordered, the atom, but they're not randomly packed together. Because nature never randomly packed together. And when it goes through slice by slice, you can see there are some orders. Actually, we use the computation method to find there are some actually hidden order. So there's an order in disorder. I mean, that makes sense, right? Nature never just pack all this randomly together. So we actually did some analysis, developed computation algorithm. We found some order in disorder. This is very medium range order, a few nanometers in length. The face center cubic-like, there's some pattern you can see here. The center atom, I showed it, each block, atom clustered. And this is hexagonal close-packed like, the body center cubic-like and simple cubic-like. So we see all this kind of order in disorder. Okay, so I think my time's up. So I try to summarize. So since the first experiment demonstration in 1999, CDI methods have been applied to image a wide range of samples in physical biology. I basically measure diffraction pattern, whether you measure single pattern, multiple pattern, overlap, and then use iterative computation algorithm to solve the phase problem, right? And we demonstrated broader CDI, allowing reconstruction of spectra, structures, and illumination probe at different wavelengths. We also developed vector typography to directly observe the topological magnetic monopoles and their interactions. And so especially I'm very proud of this work. We can see an amorphous material for the first time. I believe this field is amazing, just come consistent with the conference. It's getting so popular because images become so important. Especially you see large and small. Like in Katie's case, you see large, okay, invisible. But we see very, very small. 3D dynamics. Not only just atom, but also how the atom arrange themselves. Okay. Finally, I want to thank all my collaborators. I've got great collaborators. Actually, as I mentioned, one of them here, Laura. And one of my former students, she's now working for Facebook. She's also here. And I want to thank my funding scope, this NSF Science Technology Center, and the DOE BES, and also Muley. Now, finally, I want to mention we put everything online, with all the data and the source code. Whenever we publish a major paper, we put everything online. So try to be as transparent as possible. Thank you for your time.
Thank you, John, for the wonderful talk. So we have time for some questions.
This was a wonderful talk. Got to learn a lot. Thank you so much. I was wondering how optics-based or computational imaging-based techniques compare with contact-based techniques such as AFM, atomic.
Could you say it again? Maybe you would remember. I couldn't
okay. So I was wondering how optics-based or coherent imaging-based techniques compare with contact-based techniques such as atomic force microscopy.
Yes. So atomic force microscopy is you measure the surface. And so this is just like the surface structures. But CDI-based technique is now we can look at the quantitative structures, go inside 3D. So AFM, STM, just surface structures. Surface structures, they're wonderful, right? But for most of the samples, we want to get truly 3D, even 4D, how they change. So we can get, so the atom, actually, we see this individual atom, amorphous structures, like AFM, STM, they cannot get the internal structures. So we can get the internal structures, but also quantitative. We can identify individual coordinates of individual atoms. So that's actually very, very important.
All right, thank you.
We're running a little bit short on time, but I'll ask just one final question. So in some of the 3D reconstructions that you were showing, you needed to incorporate certain constraints on the actual reconstruction sort of itself. So how do you go about incorporating some of those constraints in the reconstruction?
So the constraints actually depend on what to work. Some constraints are very general. I'll give you one example. If you only constrain human being, right? The human being, you can define a box, 2 by 2 by 3 meter. I mean, if you reconstruct something outside the box, that's not a human being, not based on definition. So this actually we call it support is very, and then the positivity constraints. For example, the human body, it has to be positive. It cannot have some density negative. So that's kind of a general constraint. But for ankylography, for 3D, it's from 2D measurement to get a 3D shot information, yeah, that's have to use a lot of constraints. So basically, you have to know basic sparsity. How general of that method, I think it's still to be seen. This is why the community is debating, but eventually I think the concept is right, because the spherical wave, if a plane wave come in, truly plane wave come in, your eye will not be able to tell the z-dimension information. The spherical wave can tell.
Great, thank you so much, John. So I think we'll go ahead and conclude with John's talk. Thank you so much.
Thank you.
For our next speaker, I'm really honored to introduce Chang Wei Young, or as he goes by Young for short, here for our keynote today. He's my colleague here at Caltech, which has been amazing, and we've gotten a little bit of chance to work together, I hope in the future more so. He works on a lot of different areas in biophotonics and computational imaging, and lots of different spans a large range in biomedical imaging. He has many awards. I'm not going to name them all, but he also recently in 2020 was joined as a National Academy of Inventors, so among many other things. So yeah, take it away.
Thanks, Katie. All right. Thank you, everyone. First of all, I just want to thank Katie, Leti, and Ionis, and the rest of the organizing committee for giving me this chance to actually talk to you today. Like Katie said, my name is Chang Wei Young. I just go by Young, and I actually work here at Caltech. And I'm in the Department of Electrical Engineering, Bioengineering, and Medical Engineering. Okay, so before I get into my talk, I just want to very quickly first acknowledge a group of very hardworking and creative students and postdocs that makes possible a lot of things you'll be seeing today. I also actually want to especially call out Chang, Rizi, Mingshu, and Haowen. So parts of what you'll be seeing today actually is actually their recent work. Okay. Also actually want to acknowledge a group of very good collaborators I have over this past few years, especially Richard Cody, who is actually a head of pathology over at WashU St. Louis. So he and I, we've actually been working together for the past decade and a half. So again, you'll see examples of our work later on in this talk. Okay, all right. So usually this is the place where I would have a picture of Caltech and show you how nice the campus is. But you can see it firsthand today, so I don't need to do that. I want to actually just very briefly touch on the sort of stuff that my lab deals with. So approximately speaking, my lab basically do technology development in the area of biomedical optics, in the area of microscopy, as well as actually beyond the area of microscopy as well. So today, actually, what I'm going to do mostly is really talk about computational microscopy. But I just want to actually note that there is actually a large group of work that we have done actually over the past couple of decades on the use of wavefront shaping to actually allow us to actually focus light deep into tissues. So those are actually good for situations where you want to do deep tissue imaging or deep tissue, very localized optical activations for genetics purposes as well. And recently, for example, we also actually have done and demonstrated. This is actually Ritz's work, so I don't think he has a poster here, but if you want to, you can come by and see him later on, and I think he'll be very glad to show you what he's been up to in terms of actually creating a wavefront shaping system that's actually able to actually bounce light off a wall and then be able to actually focus that light into a point around the corner. So being able to actually do that allows you to do non-line of sight, diffraction-limited, raster scan-based optical imaging. All right. Okay. So, like I said, what I'm going to do today really is focus on this computational microscopy aspects of the work that my group has been doing, and mostly I think of this as a group of techniques that's good for addressing optical aberrations in imaging system effectively. But if I launch into that, right, I kind of want to actually sort of state a trend, a very observable trend associated with what is going on in biomedical optics, which is that if I look back, back when I was a graduate student, right, a lot of the things that we do in terms of innovating in biomedical optics has a lot to do with, coming up with clever ways to actually, make use of optical phenomena to actually adapt those phenomena in a way that allows us to do meaningful optical imaging in a way to actually extract more and interesting information from tissues. But if you look back at what has been happening over the past couple of decades, you also notice a very visible trend associated with what is going on in the field of biomedical optics, which is the idea that instead of actually collecting images in a way that is direct and straightforward, we actually start to more manipulatively, more sort of flexibly manipulate the way we actually collect optically derived and image-relevant information from our samples of interest. All right, and this leads to a situation where we actually had to use optics and computation in very clever and novel ways, right, to actually get to the point where we can more effectively collect data from the tissues. And again, I think all of these, right, if you want to think about this, right, has to do with the fact that computation and optics are intrinsically tied because of one thing, which is the fact that physical detectors, right, do not measure phase, all right? So your physical detectors, like a photodetector, right, you've got photons coming in, generates holes and electrons, and then you basically, detect those. But you can see that in the process of doing this kind of detection, right, you can interpret this whole thing entirely from the photon point of view. You do not need waves in order to actually understand this whole process itself. So this is entirely sort of photon picture oriented, okay? Now, of course, those of us that works in optics, right, knows that, well, there's really two pictures that you can use. You can use a photon picture, you can also use a wave picture as well. And using wave picture has its own advantages. So I'll point out, for example, the fact that if you have wave, right, you can actually, for example, apply Huygens principle, right, and be able to figure out if a wavefront that you're given, what it's going to do deterministically in the next time increment, or at whatever time increment that you want. All right. In fact, you can actually retrace its path back in time if you so will to, as well. All right. So that is actually deterministically given to you, as long as you have the wavefront. All right. It's fully predictable because it's deterministic, and it's convenient. All right. So you don't have to make measurements of that wavefront continuously over time. You just need one time point worth of information. All right. So there's really big advantages in terms of being able to actually work in the wave point of view. And of course, to actually get to the wave point of view, right, you really need two pieces of information. One is the amplitude of the wavefront, and the other one is the phase of the wavefront. And because of the fact that detectors do not actually measure, it doesn't have the ability to actually measure that phase, you actually have to somehow figure out other ways to actually get at that phase information. And traditionally we do that by applying interferometry methods to actually directly convert that phase into an intensity measurement that you can then make use of. All right, and also one other thing that I actually also want to point out is the fact that there is also that link, right, between the fact that if you're working in the wave point of view, right, optical Fourier transform becomes something that you can easily incorporate into whatever system design that you're trying to make use of. All right, so I think of this. I think of this whole thing, right, of this ability to actually get at phase, right, as being a very important part of how we can actually do computational microscopy. And back in 1980s is when FineUp actually came out with this very, very impactful paper that showed that you can actually, from a bunch of intensity measurements, right, be able to actually get at phase if you have a data redundancy or sparsity, so that you can actually trade those off to actually convert what is actually intensity information into phase information. Now, conceptually, right, if you look at that, right, in fact, that paper itself, I got to say, when I was reading that paper, right, I didn't understand it the first time I read it. And it took a couple of iterations. And I find that actually the easiest way to sort of understand the whole concepts behind it is actually through another idea that came out of it, right, which is, I think, called equation of intensity transport or something like that. But the concept itself is very simple. It's the idea that if you have an imaging system and you're able to take intensity images of an object, right, at different focal plane, right, then you can actually take those intensity information, right, and basically process it to actually allow it to then render a wavefront solution associated with the light that's actually coming up towards the imaging system itself. All right. So conceptually, right, what is happening is that you basically make a guess of whatever that wavefront is that you're interested in. So object here, you can think of it as wavefront. All right. So, and then what you do is, this gas could be horrible, all right, but it doesn't really matter. Then what you do is you basically just propagate this, right, to a focal plane that you have, a plane that you have already collected intensity information. And then what you do is you basically just replace the modulus with that measurement itself, all right? And then what you do is that then you go back and repeat it for other planes, all right? So you keep repeating this process over and over again, and then once you get to the end of this, you go back and then you do this again. You just keep repeating this until eventually the solution converges. And once you get to that converged solution, right, it not only contains the correct intensity information, it also contains the correct phase information. All right, so from something that you have made purely intensity measurements, now you actually get a solution that contains phase and intensity. And that's because of the fact that you have now traded off data redundancy here for that phase information. Okay, so phase retrieval. It's a very important concept, I think, in terms of actually enabling us to really start doing computational microscopy in that physical sense. All right, so from that, right, I kind of want to just talk about, one of the things that we've been doing in terms of actually developing a method that could be called computational microscopy, which is actually a Fourier ptytography. So Fourier ptytography is something that we developed over in my lab about a decade ago. And it really basically takes this idea of phase retrieval in combination with other things and really push it to the limit, to the point where we can actually start having a imaging strategy, right, that can actually allows us to address one of the key limitations of conventional optical microscopy in a way that basically move a problem from a physical context to a computational context. And that is the issue of aberration. So, ever since optical microscope is invented, when people were basically grounding pieces of glass to make magnifying lenses and whatnot, and stacking them together, we have always have to contend with optical aberrations. All right. So because why? There is no way that you can actually create a optically perfect microscope system with physically based optical components. All right. So and what happened is that we have been stuck with that for pretty much ever since microscope has been invented. If you want to build a higher quality microscope, what you end up doing is you end up introducing more optical elements into the objective, having more surfaces so that you get more degrees of freedom in which you can actually use to compensate for aberrations. All right. And in fact, if you take a state-of-the-art optical objective nowadays, right, you sort of cut it open, right, you will actually be able to see 20, 30 lenses stuck in there. All right. And the amount of engineering that goes into doing that, right, just so that you can actually know as much aberration as possible is really remarkable. And this is really what we have to contend with if you want to build good quality microscope. All right, but fundamentally, right, what you can do here, right, is limited, because what else can you do? Are you going to now put another 10 more lenses in the objective, 20 more lenses? You're going to reach a limit, and that. Even after you reach that limit, right, or physical limit, right, you still would not be able to completely zero out aberrations. So instead of actually doing things this way, right, computational microscopy, right, the ability to actually use computers, right, to help you address some of these issues, right, allows us to actually now take these kind of physical limitations, right, and basically convert it into something that we can use computational means to actually zero out post data acquisition. All right, so that's basically the premise of Fourier ptytography. We basically are trying to actually address this kind of optical aberrations, not in the physical sense, but in the computational sense. Okay, so I just want to actually use this to sort of more clearly sort of outline what we're really trying to do here. So this is basically a very simple imaging system. You basically have an object, you basically take the light, put it through a lens, right? So you can imagine that at some point, right, there's this Fourier plane, which basically represents optical Fourier transform, whatever this wavefront is, right? And then after that, you basically can then just take this light, refocus it down, right, into an image, all right? So there's this focal plane here. Now, if your imaging system is perfect, all right, you somehow built a perfect imaging system, then this Fourier plane, right, is directly, mathematically, just the optical Fourier transform or whatever is here. But the thing is that because of the fact that this imaging system is not perfect, what you end up with is that you don't end up with a perfect Fourier transform, but instead what you end up with is that, if you can imagine if I have a point source here, right, this optical Fourier transform would mean that I should get something that looks like this. But instead, right, it actually might look like this, where you might have some phase distortion and whatnot going on. So that's basically optical aberrations, all right? So imagine if that is happening for every point, right, then you're going to get a pretty messy picture here because of aberrations. Now, aberrations, right, in this format, right, you can sort of think of it as you can decompose it into a bunch of Zernike orders, Zernike polynomial orders. Okay, so you can basically describe this, right, as a decomposition of these guys. All right, so that's basically what we mean when we talk about aberrations. All right, so that you don't get this perfect thing, but instead you get this messed up thing. All right. Now, what we want to do is, have a computational way of actually allowing us to find this and then correct for it. All right. So to do that, I actually need to now take you back to the instrument. All right. So this is actually our earliest Fourier typography setup itself, and you can see that it's actually very simple to actually implement. All we do is we basically take a microscope, right, and instead of having a usual light source, we simply replace it with a LED array. All right. So this LED array, what we do is that we then selectively light up each of these LED. And then what that does is it basically just illuminate the sample at an angle, and effectively creates a plane wave that is sort of illuminating the sample. And then what we do is we then collect the light through this objective and then project an image of that light field onto our camera. Okay, so that's very simply what the Fourier typography system actually looks like. Okay, you don't even need to actually do a very good job of aligning things. This is why we can actually build all this out of Legos, and it still gives actually very nice images. Okay, all right. So what do you do? Okay, so in this particular system, right, the objective that we use typically is a low NA objective. So in our initial experiment, the objective NA was about 0.08. So very poor resolution, but because of the fact that the NA is so small, right, the field of view is actually very large. So that's an advantage, and I'll come back to that shortly. So where does this phase retrieval comes in? Well, the phase retrieval actually comes in this context here. So if you want to think about this, right, I basically have collected, through this microscope system, right, an image. This represents the field of view, and I have information here within that field of view. So this is basically like a poor resolution image, right? All right. So, and what you do is that as you come in your light at different angles, you basically collect similar field of view. But what is interesting is that if you think about the information that's collected here with light coming at different angles, right, in the spatial frequency spectrum, right, it actually represents circles worth of information that has been displaced, and that displacement is exactly equal to how much the angular tilt of the light that's coming in is at. Okay, so basically you get these circles of information. Now remember, when you collect this, right, you do not have phase information. You only have intensity information. So even though you know what these represents, you cannot actually just directly take a Fourier transform and then just plot them down this way, because you don't have that phase information. All right. So, but nevertheless, we know that these have overlaps in it. And that's basically where phase retrieval comes in. What we do here is that we then apply phase retrieval, applying the redundancy of these information, and basically iteratively stitch this together until we actually get to a point where all these are coherently stitched together in the way that it gives us the right phase and amplitude. So then when you Fourier transform back, you basically get back an image over this field of view, but now you actually have both intensity and phase information. Okay, so that's in essence what is going on here. Now, one other thing I want to actually point out to you is the fact that if you think about this, right, our initial raw data, right, might have poor resolution, and that can be represented by having very sparse points of information within this space itself. But anytime you Fourier transform it, right, you basically get the same number of points of information within one of these small circles. But then when you start to stitch up all of these data, right, you basically end up with a lot more points here than the points that is in one of these raw images. So what that means is that when you Fourier transform back, again, the number of points here of information has to be preserved. So now what you end up with is that you end up with a lot more points that's actually spanning this field of view. Okay, so that's one way to think about why, doing things this way, right, also gets you an improved resolution at the end of the day. And the resolution improvement really is given by how many of these circles of information you are able to fit into here. All right, so this gives you that ability. I want to just very quickly show you before I jump into the next thing of what I mean here. So basically, it ends up giving you the same field of view, but then the resolution has been improved, okay? So what you see here is that spatial frequency domain space. This represents one of these, information, low-res, information set. And then as I run this movie, you see that as I start filling in this space here, and I take the inverse Fourier transform of that, right, you can see that even though this looks really crappy and bad, I start to get high-resolution image showing up here very nicely, okay? So hopefully this demonstrates to you, right, indeed something like this, by applying phase retrieval, you can indeed basically take something that has low resolution but large field of view and create something that has high resolution and large field of view at the same time, okay? All right, so this is basically, an illustration of what we can do. So with a 2x objective, which has a large field of view, if you zoom into it, not surprisingly, the image raw data looks, very poorly resolved. But by applying this FPM type method, you can actually start to stitch the information together and get high resolution image out of this whole thing. All right, so with this, right, we can actually, by taking a couple hundred images, stack things together in such a way that we can actually improve the resolution really quite significantly. Okay, so again, this is a picture showing just a HAD blood stain, and you can see that the raw image looks horrible like this, but then once you do Fourier cytography, you can actually resolve and provide large field of view, high resolution image out in one shot. Okay, all this thanks to the power of phase retrieval and the ability to have powerful computers to do this kind of computation. All right, so I talked a lot about this whole idea of Fourier cytography, but remember when I started this, right, I talked about the fact that Fourier cytography allows us to more flexibly deal with aberrations, right? So what gives? So how does that all fit in? Well, the way it fits in is the fact that during this whole process of doing this Fourier transform into that space and then Fourier transform back, right, you can actually impose within it a pupil function that reflects how imperfect the imaging system is. All right, and you may not actually, in the first place, right, know what that pupil function looks like, but you can actually tell the computer that there is existence of that pupil function. Go figure out for me what that pupil function looks like. Go figure out what the aberration looks like. All right, so you can actually build into FPM that part of the algorithm. And in fact, this is actually an illustration showing just that. So if I don't actually tell the computer, right, there is aberration within the imaging system, right, then if you stray away from this center point of this imaging system, microscopy system here, so typically, right, if you look at the center of a image, right, resolution tend to be good because aberrations at that point tend to be low. It's only when you stray away from that center point, right, that the aberration starts kicking in, all right? Oh, by the way, another thing that I should mention is that pupil function, right, is dependent on where on that field of view you're at. Okay, so typically in the center, field of view is, pupil function is nice, and then as you stray away, they start going bad, all right? So this is why we picked this point here. So if you look at this, right, without aberration correction, the FPM actually gives you a horrible image. But if you actually tell it, right, what the physical aberrations of the system is, so this is where we actually went in and physically measure what the physical aberration on a microscope is, and then put that in as a solution, you can see that it actually gives a pretty good reconstruction where it corrected for the aberrations. All right. But remember, I also said that you may not even know what the aberration is, but you can also tell the computer just to go and figure out. It turns out there's enough redundancy of information in the data we collect that it can actually do just that. So this is a case where we actually simply tell the computer, there's aberration in the system, go figure it out for me. And it was actually able to do that and be able to correctly generate a high-resolution image out at the end of the day. All right. Okay, this picture, right, basically just shows you, right, that aberrations has chromatic aberration components as well, meaning that the pupil function may not look the same at different wavelength. And indeed, you can see here in this particular examples, right, at different locations, not only is the pupil function different across the different locations, but it's also different at different colors as well. And FPM can actually figure that out, correct for it, and give you the right image at the end of the day. Okay. All right. Having said that, let me just show you how you can actually take this. So aberration correction, great. So that means that you can actually, in fact, don't use a perfect microscope. So don't have to try to use a perfect microscope to do your imaging anymore. Instead, you can use something that might have aberrations and just computationally correct for it after the fact. There is one actually very important consequence of doing that. That's overridingly important for pathology. So, and that is the idea that your defocus, your image defocus, because you didn't have your object at the right focal plane, can be thought of as an aberration, okay? And so what that means is that you can actually use FPM to actually correct for that defocus dynamically as well. And this is actually an example showing just that. So we basically have the FPM collect the information, and then what it does is that basically we just tell the FPM to computationally put everything in focus. So this is a case where what this is a fine needle aspirate. So fine needle aspirate is basically the pathologist sticks a needle into the patient, take an aspirate of tissues, and typically when you do that, typically from the thyroid gland, you basically have a bunch of cells that sort of sparsely populating, a mass of tissues. This tissue typically is meaningless. It's just a mass of meaningless stuff. But you have all these cells that you really want to see. All right, and typically, right, this is what you see if you put it under a microscope system here, because you get to choose only one focal plane. But this thing is a mass, so there's cells that are in focus and cells that are out of focus. So that's basically what the pathologist has to contend with. And this makes it very time-consuming for them, because typically they would have to sit there and manually tune their microscope, see all this different focal plane to figure out, what is going on. But what we've shown is that you can actually basically do an FPM collection of this, and it basically just generate for you this all-in-focus image. You can see here all these images. Even this part here, right? You think you basically put everything in focus already. Not really the case for the standard microscope system. But with FPM, we can really put everything in focus. This was out of focus here, but it's in focus here. So this is really useful for that kind of pathology application. And one thing to note here is the fact that you may say, all right, so yeah, fine, this thing is thick. So why not just take a Z stack of images and then, and then just pick the ones that is sharpest in focus? Well, the problem with doing that is the fact that you basically end up having a situation where the number of Z slices that you have, right, is still finite. You can't go in and possibly take an infinite number of slices. So what that means is that you still would have step jumps in terms of planes of focus associated with that tissue section itself. But with FPM, right, you can actually gradually tune your defocus continuously, so you don't actually end up having that issue. One other thing is the fact that basically, right, the FPM basically collects. It does collect redundant data, but it only collects about 4 times the redundant data as is equivalent to one single slice. All right, so basically, the amount of data that you had to collect, to actually allow you to do this sort of flexible focus correction, right, is still much less than what you would otherwise have if you have a Z stack, where you might actually end up having to take 20 or 30 slices in order to actually be able to actually fidelity, generate this kind of image. Okay. All right. So one other way that being able to actually correct for aberrations, right, is that it also actually allows you to start to actually build what we characterize as parallel microscope system. All right, so really this thing is actually enabled by 3 things. One is the fact that you can actually make plastic lenses very cost effectively. You can actually, in fact, contract out and get something like this made very cost effectively, all right? But problem with this is that, the aberration is bad. All right, this is not good quality lenses that you end up getting, when you do this. The other thing that actually is enabling us to actually do high quality parallel microscopy is the fact that you can actually get camera chips very cost effectively, purchased nowadays. So you can get these good quality, chips, right, for a couple dollars to $10, very cost effectively. All right. And then in combination, right, we just talk about Fourier typography, which is basically a method that allows us to computationally zero out aberration. So what that means is that these two works really well together. All right, you can start to think about the fact that I can end up using very bad quality lenses and then just use computation to correct for that. All right, so this actually led us to two projects that we did that demonstrate this utility. So the first one, right, we didn't use plastic lenses yet. All it is basically we just use some very cost-effective objective lenses. Not very good quality, but nevertheless objective lenses. And what we did is we basically took a bunch of them, put this together. So this the real estate size is actually, footprint size is actually very small. And what is nice is that we can then actually use this, right, to actually monitor things that is growing in cell culture plates very nicely. So we can actually stick this whole thing into an incubator, put in the LED array on top of it to illuminate it for FPM purposes, and then it's ready to go. So this actually allows us to achieve this kind of characteristics. All right, field of view is still pretty decent, about 5 millimeter by 5 millimeter. Resolution is about 1.2 microns, and if you actually want to do fluorescence, you get about 5 microns resolution. All right, so with that, we're actually able to work with our neuroscientist collaborators on campus, and be able to actually allow them to actually track the progression of neuron cultures over a period of 3 weeks. So he was able to stick this into his incubator and then be able to see the growth of these neurons very nicely throughout that whole 3 weeks. The field of view that I'm showing you here, by the way, is tiny. It's just only about, this is 20 microns. The actual field of view is actually much larger. So like I said, about 5 millimeter by 5 millimeter. So you can see and appreciate the fact that this really allows you to collect a lot of data, good quality data in this context. So one other thing that actually I want to note here is the fact that so far, until now, right, I've been showing you bright field images that FPM generates, right? But in this case, right, these images are actually phase images, okay? So not surprising that we can generate this, because why? When you do phase retrieval, you get the phase out automatically. So you don't need DIC or anything, you can actually just do this and you can get phase automatically, okay? All right. And then we were actually approached by Amgen about the fact that if we can actually do this, right, can we just do this not for just 6 wells, right, but can we do this for 96 wells? All right, so this really is when we started pushing and started to actually implement this kind of imaging system with plastic lenses. So we actually contracted this out. Somewhat we were able to actually design this lens so that it's very compact. It contains about 4 lenses in them, and 4 lenses, plastic lenses, doesn't give us very good aberration correction qualities, so it's still a pretty bad objective. But nevertheless, right, the nice thing about this is that these are cost effective to create. All right, so we actually made a bunch of these. We basically were able to also high density wise pack them together very nicely so that we can now image simultaneously all the wells in a 96 well plate in one shot. All right, this is just to show you, the assembly of it. And then, like I said, right, you can actually get these camera chips very cost effectively as well. So we basically, again, created a system with 96 of these CMOS sensor chips stacked onto a circuit board and was able to read it out. Okay, now, all of this, not surprisingly, generate a lot of data. So we actually have to have a very souped up GPUs that was able to take all this data, do the processing, and then store it accordingly. I think we actually end up spending about 2 months just building the water chilling system just so that we can actually cool this thing appropriately. if you ask me, I don't think I will ever want to do this kind of project ever again, because why? It turns out the optics is very easy, but the whole other aspects of all the engineering was actually tedious. But good thing was I had a postdoc at that time that you know, to him, this was great. Anthony Chan, by the way, fantastic engineer. So he was able to actually take all of these and really put these things together very nicely for Amgen. All right, so, okay, so again, the specs are listed here. And this is basically the performance that we have. Now, you might wonder, right, why did we even bother doing this? Surely they have 96 well-plate microscope imaging system out there already. Well, the reason we did this, right, has to do with the fact that typically what is out there, right, is again built typically around a high quality microscope objective that they then scan across these 96 well plates. So you can appreciate the fact that because you have only a singular imaging system, right, this kind of imaging, right, takes a long time to actually do the whole plate, or you have to sacrifice the dwell time at each plate, so you might not collect strong enough fluorescence images that way. All right, so by doing things this way, right, you can actually have 96 microscope system looking at each of the wells. Each well on the well plate is basically has a dedicated microscope, imaging it, so you can actually do things much more effectively and efficiently. So when you actually plot out in terms of this sort of imaging throughput plots, right? Again, I'm just going to go through this very quickly. You can see that this our 96i system, right, actually sits right here in terms of its performance. So so it really is. By the fact that we're actually parallel processing is really giving us that advantage of being able to do things in a very high throughput fashion. Okay, again, all this enabled the fact that you now can do plastic lens very cost effectively, camera chips very cost effectively, and then Fourier typography to correct for aberrations. All right, so just want to show you very quickly some of the images that we're able to see. So you can take these kind of 96 images in one shot, zoom in, and you can see the Fourier typography images, and then as well as the raw fluorescence images. I should also actually note at this point that Fourier typography allows us to actually correct for aberrations in the bright field images nicely, but it doesn't do aberration corrections in the fluorescence images. But the fact that you can actually get the pupil function of the microscope system, right, from Fourier typography means that you can actually then take that and use that as a way to do the deconvolution of the fluorescence images so that you can actually get to at least the numerical aperture limited resolution of the fluorescence images this way. Okay? All right. Okay, so I just want to actually touch on one other thing that came out of our adventure in the Fourier typography, which is we started asking ourselves, what is the worst imaging system that we can think of and work with? Well, turns out eyes. All right, eyes, just a single lens. Okay, and then you have your cornea and all that stuff, right? But not really a lot of optical surfaces. And the aberrations associated with organic eyes is actually very significant and very significant, all right? So it is a very poor imaging system in the context of optics, all right? So we decided that, we can actually apply the idea of Fourier typography to try to correct for the aberrations in the eye so that we can actually then get high resolution image of the retina in the back. And I, again, don't want to go into too much detail about this. So we're actually able to, 3 years ago, finish up an experiment that shows that you can indeed do this kind of aberration correction with a modified Fourier typography system. And this basically shows you that, this is a model eye, and you can see this is the poor resolution image that you get because of aberrations. But then if you go in and correct for the pupil function, you can actually get high resolution images out subsequently. All right. And again, we were able to actually work with a sedated monkey, and we also show that you can use this method to actually get well-corrected retinal images from the monkey's eye this way. Okay. All right. Now, Ever since we developed and published on Fourier typography, numerous groups around the world have taken it up as well and have done some really interesting and significant stuff with it as well. Last year, we actually published a paper that we hope at least a survey, broadly some of these ideas. And I would welcome you to check out this paper if you're interested in reading more about other developments in Fourier typography. I do want to actually take this time to highlight 3 examples of things that I thought was really interesting. So one is actually by Laura Waller's and group. I think at that time Lei Tian was there too. I heard that Laura Waller is here. I don't know where she is. Oh, okay, somewhere. Okay, someone is pointing. All right. Okay, hi. Okay. All right. So, so this is actually I thought it was a fascinating idea because when we first published on FPM, right, we only turn on one LED at a time and then sequentially do scans. And what she and Lei Tian was able to show is that if you actually turn on multiple LEDs, you can actually effectively trade off either sparsity in the image itself or SNR, right, to do actually quicker imaging. So this is a good example where their group was able to show that if you do sequential lighting of the LEDs, you can get images like this after scanning for about 600 seconds. But then you cut that time down very significantly by multiplexing 4 LEDs at the same time. All right. So I thought that was really cool and interesting. Now this next one, right, has to do with the fact that instead of actually illuminating the sample with effectively at sort of plain illumination on sample, what Guan Zhang, who by the way actually was one of the key inventors and players in my group when that developed the FPM about a decade ago, he then went on to actually start his own group. He was actually able to show that instead of doing it this way, you can actually impose a speckle pattern on the sample. And then use that speckle pattern, right? And the fact that there's high spatial frequency components within that speckles to actually, again, collect things in a sort of Fourier typography way, and then be able to actually figure out not only the speckle pattern itself, but as well as a high resolution image of the object at the end of the day, okay? All right, so that again is, I think, very interesting because why? You can actually, if you want to apply near field type methods, right, to actually get very high spatial frequency contents, near field speckles on the samples. So that actually I think is a very interesting way to do things. All right. So one last thing that I kind of want to actually talk about is this, in this context of what others have done, is the fact that there's also actually a very consistent, use of deep learning recently, right, in Fourier typography ideas. So I want to highlight this one, which is by Lei Tian's group, where instead of actually, using sort of face retrieval in the traditional sense, right, what he did was he basically trained a deep learning network, right, that was able to just take raw data and basically just output the final process image itself, which I thought is actually a fascinating way of using deep learning to actually replace this whole retrieval process. One other thing that came out was from Rook Horstmeyer's work with Benjamin Jakovich. So again, Rook was actually one of the key inventors and players in FPM, back a decade ago. So he graduated from my group, and then he went on to a faculty position at Duke. So this was actually done during his postdoc period, where he actually showed that you can use deep neural network, right, to actually optimize your illumination scheme so that you can actually do things in a way that allows you to highlight important sample features within the sample that you're interested in. So basically, for example, changing the exposure time in which you actually turn on a particular LED and whatnot. Okay? So I think those are actually very cool and interesting ideas of using neural networks in Fourier typography. I want to actually now sort of spend the next hopefully 15 minutes talking about some of the recent things that we've been doing, where we're not necessarily sort of trying to put deep neural networks into the physical layer of Fourier typography, but to sort of take a step upwards, right, and talk about how the kind of data that Fourier typography is able to generate, right, might actually be useful in novel ways in the way we actually do deep learning processing of image data down the pipeline. Okay? All right. So so this is my, I'm not a deep learning expert or anything. This is my naive understanding of what deep learning is about, right? So traditional machine learning, right, you typically have to sort of manually annotate and say, all right, look for circles. You tell the machine, look for circles, look for squares, look for edges, primitive features, right? Then you allow the machine to then hold on to these features, right, and then basically tune its classification network so that it can actually use components of these kind of basic features, right, in order to actually generate its classification. All right, so this is basically what traditional machine learning is about. So deep learning, right, is different in the sense that instead of actually having this manual feature extraction, right, you actually incorporate that into the neural network itself. So you don't actually have a human involved in this process, but instead you let the deep learning system utilize self-learning to figure out what features are interesting to look at. All right, so one thing that this actually is very useful in one of the things that we've been doing with our pathologist collaborators is the fact that he basically have a platform in which he basically traps circulating tumor cells from blood onto filters, and he basically analyze these to actually tell things about the tumor conditions of a patient. So the problem is that because of these filter holes that is on these filters, right, generally this machine learning, traditional machine learning methods actually have a hard time identifying the circulating tumor cells itself because it sometimes actually confuses these holes for the cells of interest. But what we found is that the deep learning actually doesn't have these issues when we actually apply it to actually look at these kind of analysis. Okay, all right. So this is why I actually really like deep learning. It's self-learning, so let it figure it out, and it turns out to be highly accurate. Now, I want to actually now point you out to something that makes me really, really excited about deep learning, and why I thought even though I don't know much about deep learning, this is an area really worth spending time to investigate and research on. So this is actually a fairly obscure example, but I actually encourage you to read this paper. In fact, what I'm going to talk about is only a minor point in that paper itself, but it really wows me, which is the fact that basically they took a bunch of retinal images of patients. These are patients, so they know the gender of the patients. And then what they did was they basically trained a deep learning system, right, to identify the gender of the patients based on these retinal images. Now, if you pose this question to a human, right, we probably will go, what? How am I going to look for the gender of a patient through this, right? But it turns out, right, if you do this, you give it to a machine and train it on it, right, it was actually able to identify the gender of the patients with over 95% accuracy, which is really astounding to me. And what is also furthermore astounding is the fact that even though, right, we can actually generate a attention map of what the machine learning was looking at in this image itself, right, we still do not know exactly what kind of exact patterns, right, the machine is actually honing on in order to make that identification, meaning that the machine cannot teach us humans what to actually look at in order to make those identifications. So that really points out that our vision actually have limitations. And I'll give you an example. You take an image of a person's face and you turn it upside down, chances are you won't be able to actually recognize what that face is. All right, so even just that 180-degree shift, right, poses a signal limits to our human vision's capability. So this really, I think, points out to the fact that, at some point, right, in pathology, if we actually are looking for very subtle patterns, right, you actually probably be better off deferring that task to a machine to actually do a better job of. So these are strengths in machine learning that I'm actually very excited about. So. This actually started in the beginning of summer, and I think Yuan, who is the one that did this, is probably in the audience. This really sort of highlights, that power of deep learning to do something that humans may not be able to do well at all at any given point in time. And what this project is really about is our collaborators actually provided us with biopsy slides of patients with lung cancer, a very specific kind of lung cancer, which is non-small cell lung cancer. It's the most common and most dangerous type of lung cancer. These are the patients that ends up having very high fatality. So the question that we wanted to address is, given these biopsy slides, so these are old biopsy slides. They were taken a long time ago. So the pathologist actually knows the outcome. They know whether those patients, right, from which this biopsy has been taken, right, progress or did not progress to have metastasis. So the metastasis that they are particularly interested in is brain metastasis, because that's a very common metastasis that this kind of lung cancer patients develop. So they know whether they progress or not. But if they just are provided with the biopsy slide and asked to make a prediction whether in 5 years the patient is going to develop brain metastasis or not, the answer is pretty much a random coin toss. Okay, they cannot actually draw any conclusions at all. But it turns out that if we give enough of these data, right, to the machine, right, the machine actually was able to predict whether that patient is going to progress to have brain metastasis or not with over 90% accuracy. So this is actually currently still in progress, and we have been actually trying to break this model for the longest time. We could not find how the machine was doing this, but it was consistently doing this with very high degrees of accuracy. And one of the things that we found actually quite surprising to the pathologists when we actually showed them the results is the fact that typically a pathologist, when you look at biopsy slide like this, they typically go in and look for the cancer cells and look at the condition of the cancer cells. But instead of doing that, right, the machine seems to be looking at the things that are outside the cancer cells, the connective tissues, the stroma that's outside the cancer cells. So this is really counterintuitive to them. And again, even when they actually start looking at those, right, they could not make head and tails out of how the machine was able to make such excellent prediction by looking at what they were looking at. I just want to very quickly show you this slide, which is basically a TSNE plot, right, showing that, you know, this is how the AI was able to separate them, right? So you would think that if you have something like this, right, you can then say, all right, if I look at the control and look at the ones that progress in brain metastasis, right, maybe I can train, the pathologists, right, can train themselves to actually tell the difference. But again, it turns out not to be the case. So this is really a case where currently the deep learning ability to do sorting, right, is defying human interpretation. And again, I think this harkens back to what I just said about the fact that, you know, humans' vision has limitations. And I think at some point we actually need to recognize and understand that and realize that, you know, some of this stuff that might be going on in deep learning, right, may not be something that we can fundamentally understand in a level that we can interpret well. All right. So I said all that, right, because again, I want to show you why I'm excited about deep learning. I want to actually show you now why I think Fourier typography, right, is actually a good match going forward with whatever deep learning might be doing. Which is the fact that deep learning, right, has an issue with defocus. So typically, right, if you take a standard microscope image, right, it might look something like this, high resolution here, but then because the sample isn't quite flat, right, you get poor resolution here. And this is a problem for you know, AI type system, because when you have things like this, right, it's basically just garbage in, you basically get garbage out. All right, so something like this, right, where you render everything in focus, right, will give AI much easier time, I think, in order to actually do the processing. Okay. Okay, one other thing that I think is worth noting about FPM type imaging is the fact that we can not only just get bright field images, we can also get face images. And typically right now, if you give this to a pathologist, it means nothing to them. They're trained on this, and that's it. Okay, this is not something that they can interpret. Again, you know, connecting back to the fact that human vision is very limited. But if you give this to a machine, right, this is extra information. You know, it doesn't have any bias about the fact that you can only work with this. So if you train it well enough, right, you should actually be able to use these information to complement each other, you know, to hopefully draw better conclusions out of what you're showing it. All right. Okay, one last thing, which is, you know, again, connecting back to what I just said, right, about the fact that human vision has limited to it. So if that's the case, right, why do we expect that human-oriented data, right, is going to be optimal for AI? Why is it that we think something like this, right, is what the AI would like to optimally do processing with, instead of maybe like a Fourier transform of this image itself? All right, so that's a stretch, but again, I hope you see my point about the fact that we maybe actually want to start thinking about designing imaging system that's tailored for AI use, and that may mean that we may need to leave human interpretability out of the design specs itself. And again, hopefully, optimize the design of the imaging system, right, so that we can avoid swamping the fact that AI input nodes are actually still finite in numbers. All right, it's not like they have an infinite number of input nodes, so you still got to put in data in reasonable chunks for it to do processing. So I think this really points to the fact that over the next decade or so, we really should start to think about designing integrated AI architecture with the imaging system integrated as one. All right. I just want to now take a couple of minutes to summarize what we've talked about. So we talk about the fact that Fourier typography moved the problem of aberration corrections from a physical regime into the computational regime. And this allows us to get high resolution as well as large field of view images in one shot. So effectively allowing us to expand this spatial bandwidth. So spatial bandwidth is just a fancy term for the fact that you get high resolution and large field of view at the same time. And then basically, you can think of it as number of resolvable pixels. And then it also has this ability to do refocusing because defocus is basically an optical aberration. Allows the use of cheap lenses with poor imaging quality, right, to do parallel microscopy imaging, making it practical. All right, and going forward, I think that Fourier typography and deep learning are actually a good fit together because FPM can provide all-in-focus images for deep learning processing. The phase information that we collect from FPM is difficult for humans to process, but it is additional information that can be provided to deep learning for processing and getting high accuracy. The compact data efficiency nature of FPM is also a good fit, I think, with deep learning. And then more broadly, we should be thinking and designing microscope system for AI processing, which may not necessarily mean that these images at the end of the day are human interpretable. Okay, I think with that, I thank you for your attention, and thank you.
Yeah, thanks so much for the fantastic talk. So questions? Oh, we have one already.
Thank you so much for the talk. It was amazing. I especially found the metastasis results to be super cool. So I had a question about that. Metastasis essentially happens when cancer cells break through connective tissue.
That's right.
And it makes sense that a deep learning algorithm can estimate stresses in the tissue for them to break through. But it's also a temporal process, right? So I was wondering if there is any value to adding a temporal dimension to deep learning for that to get higher accuracy.
So are you asking about looking at larger scales? Is that what you're asking?
Yeah, a larger time scale.
Yeah, so I think we really only have just started touching on this, but you're right. Looking at different scales, I think would be actually very interesting. Looking at how even normal-looking type of tissues, right? And this is actually something we kind of started to see as well. Even though they don't contain cancer cells, right? If you train a machine on it, right, it can actually potentially still make high-level prediction about whether something is going to metastasize or not. And that, again, to me is kind of surprising. But again, I think it's actually what makes it so valuable and worthwhile to actually look at things like this. Again, really coming back to the fact that what we humans think of as meaningful may not be what I think machines are going to think of as meaningful.
I see.
Okay.
So in the last thing you mentioned, it was like even if you look at a part that doesn't have cancer cells, you are able to tell. How is that? Because cancer is typically a random mutation, right?
Yeah. So there is a hypothesis in pathology, although this is kind of speculative, right, about what they call cancer field effect. So a cancer might develop here, but in its neighboring tissues, right, there are also biochemical changes that could be occurring as well. And that might be something that the AI might be able to pick up from normal-looking tissues that give them enough cues to make prediction out of it. So again, all of these are, if you really want to sort of really dig into this, right, the pathologists have a lot of insights and crazy ideas. It really is, I think, a very good time to really bring AI at the next level into pathology and really start making some sense of these theories.
I see. Yeah. Thank you so much. Really cool work.
Thank you.
Hi, thank you. I was really inspired by your talk, and I'm also very interested in some of the applications you're working on. My question was more about the earlier work you presented when you were first applying FPM to tissue samples.
Right.
Did you have to use any priors for the phase retrieval to work, and if so, what were they?
Okay, so no, because the phase retrieval sort of takes care of it. There is a assumption that goes into it, which is that the sample is thin enough so that it effectively functions as a 2D sample. Okay. It doesn't have to be flat, because that's where the refocusing actually comes in. So you can think of it as, if you give it a book, it will not be able to do well. But if you give it a crumpled piece of paper, FPM will be able to do well in that context, because it's still 2D, even though it's crumpled.
Okay, thank you.
You're welcome.
And first, thanks for the wonderful work and presentation. I just regret that I haven't read your paper yet. Okay. So I have a very fundamental questions. And when you propagate the waves from one layer to the other, right. And do you use Fresnel diffractions approximations and assume that they are coherent light? But the fluorescent are incoherent. Right. So how do you manage those equations?
So phase retrieval doesn't work with fluorescences. It only applies in bright field type context. So Fourier cytography is a bright field method. Basically, it's a non-fluorescence method. Let me put it this way, because FPM, we also talk about bright field and dark field modality as well. But it doesn't work with fluorescence. Okay. All right. Yeah, we can talk more about this offline as well. So there are actually subtleties in this that I can sort of walk you through in more details as well.
Thank you.
Okay? All right.
Hi, great talk.
Thank you.
I have a question related to the summary slide. So in the last point, you say we should designing microscope for AI processing. So it's more like you want to have a code design of your hardware and software. So do you have any, can you provide some insights on this direction, just some general insights? And also maybe some example will be, you will design some you can fabricate the weights of the neural networks, like the diffraction neural networks talked like yesterday by Professor Osgan. Right. Can you comment on this?
So that last one is indeed
exactly.
It's wide open. So at least from our starting point, right, we can start to think about because we can with FPM get amplitude and phase very efficiently, we can maybe start to think about instead of actually presenting it as a spatial domain information, what if we present it in some other domain, like spatial frequency domain might be one, but there might be other transform that we can do in order to actually present the data, and how is that going to help optimize the way that the AI might be able to do processing? Again, I think this is going to be a long-standing problem of how we can intelligently go about doing this. It may be a case that we cannot intelligently go about doing this, and we might have to design AI to actually get at that kind of questions. But I think that, again, is something that we really need to start looking into along this line, where we're no longer limited by human interpretation, but to design things in a more general, information-oriented way.
Okay. Thank you.
Yeah.
So we're running short on time, so one last question, and I'm sure there's many others, but hopefully you take it offline.
I think, maybe he can ask it, because my question is kind of similar.
Go ahead.
Okay. All right.
Yeah, thank you. Very great talk. So actually, I feel pretty nervous to ask this question. Okay. So because I come from an AI background.
Okay.
So when we designing AI, using machine learning, deep learning, microscope, so we found our training data, because AI is trying to find correlation rather than inference or causal inference, right? So they're basically, we found a lot of artifact when we seeing the reconstruction result from our AI approach, macroscope reconstruction method. So I'm wondering, as a macroscope, as a measurement tool, which the future, the biological scientists, they need to use such tools to, based on that facts, to develop their theory. So I'm wondering, what's your comment on how do we really know what we are measuring is correct? Like if we use some like AI master. Thank you.
So there's multiple layers to that question. So I guess I would have to say that the layer that, okay, I'm going to very generally answer that question. So that's a good question. It's actually a pretty deep question too. I guess I want to say that a lot of times, right, especially in the context of pathology analysis, right, we know there is a ground truth to things. We know that, what we want, right, is ability, right? For example, in this particular project, right, the pathologist wants to predict whether something is going to lead to brain metastasis or not, right? So there is that ground truth that we can ground things on. And maybe along the ways, right, we don't no longer need the AI to actually, look at the images itself, but, look at some other subset of, whatever information that we're giving it to it, right? I think that's how we want to think about this, how we connect that to that, input, right, to the final outcome prediction that we want. And if we can do a good job on that, right, that at least at some level, in the practical sense, right, is good and well for the pathologist. So.
Yeah, thank you. So it's basically like if we have a ground truth for some like data, so like we can have some way to like judge the model, and then like if this model is good enough, like we can apply it. Okay, thank you.
Right.
Let's thank our speaker one last time.
Thank you.
Great, so we're gonna head into, actually we're gonna do our group photo right now, followed by lunch. So just a few instructions. So we're gonna take the group photo right outside of the auditorium.